I will talk about our main method, which is combination of density functional theory and dynamical mean field theory, and its application for real strongly correlated materials. Formulation of the method. First, what is dynamical mean field theory, why it is needed. Then, technical but very important question, Wannier functions as a choice for localized atomic-like orbitals. Determination of Hamiltonian parameters and constrained DFT calculation for Coulomb interaction parameter. And then DFT plus DMFT calculation scheme. The major part of my talk will be applications. First, strongly correlated metal, strontium vanadate. Then metal Z transition vanadium 6 oxide. Heavy fermions in D materials, lithium vanadate. The charge transfer insulator nickel oxide. Metal Z transition with pressure in manganese oxide. Very interesting story about correlated covalent insulators, iron silicide. Pnictide superconductor. Young-Taylor distortion in copper fluorine. And F electron localization in metallic cerium. So first, why we need to use something above DFT at all. Let me see how to switch off those. That's it, I see. So here you can see that DFT will give us half-field bands. Yeah? DFT plus U, which is actually Hartree-Fock, will give us separation insulator, low Hubbard band, upper Hubbard band. But the most interesting case is when we have so-called three-peak structure, two Hubbard bands and quasi-particle band. To treat this problem, correlations, which mean that electrons are filling each other, not as a mean field theory, but every electron knows which side is occupied and which side is unoccupied. The model consists of two parts, kinetic energy part, which is hopping with T parameter, and Coulomb interaction part when we have two electrons on side with an energy U. Unfortunately, there are no real solution for this problem, lattice full solution. So that quite long ago, that moment. There was proposed by Dieter Folchert and Messner the mapping of the lattice Hubbard model on Anderson impurity model with effective hybridization with the medium. The problem is that this medium is not a real medium. Why it is so appealing? Because single impurity Anderson model spectral functions has simultaneously Hubbard bands, satellites, and quasi-particle peak. So the idea is to replace all the neighbors of this one separate site by effective medium, which is described by hybridization function. Okay? And that is key part. We have some hybridization function. Then we calculate green function. Then we introduce self-energy corresponding to the hybridization function. Put this self-energy on every side in the lattice. And then again, we go to impurity problem. So repeat, we first define effective impurity problem with some hybridization function. After define from this self-energy, which is effective potential, complex energy potential on every side. Calculate new lattice with this potential, and then again impurity problem. So that a self-consistently defined effective medium. That is the idea. Now, here we have model calculation. First, we have U0, non-interacting case, half-filled bands. Then we switch on interaction, Coulomb interaction on side, which doesn't make much except of giving these shoulders. And here at last, famous three-peak structure, when we have well-defined lower occupied and upper unoccupied Hubbard bands and quasi-particle band. The problem in applying it for real materials is to define parameters. Just TU and so on is good for any model calculations. But when we have real orbitals and degenerate Hubbard models, that we need to take from somewhere parameters. Kinetic energy part is quite easy. If we have bands, then we have T parameters. No, it is not one T parameters, it's a lot of them, but nevertheless, we have them. The problem is where to take from Coulomb interaction parameter U. First of all, in Hubbard model, we say some atomic orbitals, not specifying what it is. In real calculations, we should have them in explicit form. And the best choice would be Wannier function. First of all, there are localized orbitals and orbitals centered on atoms. So that they have the same symmetry as atomic orbitals, but they are not atomic orbitals. And they are done by unitary transformation from Bloch function. So we start from Bloch function, and by unit transformation from them, we have which are distributed over all crystal, and we obtain localized atomic type Wannier functions. The problem is how to define this unitary matrix. And that is done by projection. So we choose atomic orbitals, which could be anything. For example, in pseudo-potential, that's pseudo-atomic orbitals which are explicitly present in the potential. Then project then on block function and then make linear combination. Tell how when a function looks like. That's for strontium-108, and when a function is d orbital centered on the atom plus addition of p orbitals on oxygen surrounding it. So that's very important. So that our Wannier function are not just atomic orbital. They know about hybridization with oxygen, for example. Also, there is an ambiguity in defining Wannier function. In the left side, we used full set of bands, oxygen bands and d bands. And in the result, we have practically atomic type Wannier function. But if we will consider only d bands and forget about oxygen bands, then we will have explicitly addition of oxygen to Wannier function. And here is the most interesting story of how can looked like Wannier function. So we have oh, that's it, yeah. So we have the so-called 1/8 doped copper vanadate. So we have 1 hole per 8 coppers. It's very interesting story with stripes. And the whole density, here is percentage of the whole density, will be very widely distributed. From the bands, we have one band which is half occupied. And that is how Wannier function looks like. So it is centered on oxygen, so on the bond, copper-oxygen-copper bond. Yes, that's it. But it's not only so. Every copper d orbital is surrounded by oxygens, and also we have something as a third neighbors. But that's very rare case. Usually, Wannier function looks like atomic orbital plus something. Now, how it is calculated Hamiltonian? Hamiltonian in DFT could be quite large, especially if we have plane waves, plane waves basis set. So now we again make projection, or in other case, we calculate Hamiltonian matrix elements using Wannier functions. In this case, we will have a Hamiltonian now not in plane base, but in Wannier functions, which is relatively small comparing with plane waves. That's how it looks like. Blue bands are full bands, which included oxygen, D bands, sp states, and so on. Now, if we are interested only in T to G part of the D band, that is this red one. And now, as you see, the procedure which I showed immediately separate for us red band from blue band. And that's the same case for density of states. So again, we make not any approximation. We just construct Hamiltonian and bands from Wannier functions, nothing else. So no approximations at all. And now how calculate U? In this case, we calculate diagonal Hamiltonian elements, diagonal density matrix elements, and define them as an energy of any function, an occupation of any function. And then we run constrain DT calculations and define Coulomb parameter U as a derivative of the energy over occupancy. Now full DFT calculation scheme. We start from some approximation for self-energy sigma. It could be 0. And then we calculate integrating over Brillouin zone local green function. Then we write Dyson equation. We exclude from green function sigma and obtain Bass green function, so-called green function, which define surrounding media. Then we solve interacting impurity problems. That's important. We define medium, then solve as good as we can by quantum Monte Carlo, for example, impurity problem, obtain new green function, and then using the same Dyson equation, we obtain new approximation to self-energy, then go to lattice calculation. That's it. And then we repeat it self-consistently till everything will stop varying. So that is the method. Now about applications. Why is this strontium vanadate is so popular and important? Because here we have one electron in partially filled T to G band. That's it. As simple as can be. Now, and here, that is the result of calculation, we have typical 3-band structure, which is known from the model calculation, but that's not model, that's real material. So we have occupied lower Hubbard band, unoccupied upper Hubbard band, and partially filled quasi-particle band. And here is comparison with experiment. First, there's XPS spectra, which shows the distribution of occupied states, and inverse photo emission, which shows unoccupied. So you see that all these speculations about low Hubbard band, upper Hubbard band, quasi-particle bands, the peak structure is immediately seen experimentally. So DMFT, LDA plus DMFT reproduces it successfully. And here is spectral function. We also can calculate spectral function, K-resolve spectral function, using this formula. And That is the second important part of correlation. First, as I said, is appearance of the shoulders or lower upper cover band. And the second is a narrowing of the band. So black ones are DFT calculation, and red ones are spectral function obtained in DMFT. As you see, it's nearly 2 times more narrow than DFT band. And that's the most important, because it gives narrowness band and gives increasing effective electron mass. And both of them can be measured experimentally. And our calculations are confirmed by experiment. Now, the most interesting story is mode insulator, a mode insulator transition. And interesting story is that normally, if the material goes from band metal to insulator, then immediately some ordering happens. For example, here for V203, if you will go here, that will go from to antiferromagnetic insulator. But it is possible to go from paramagnetic metal to paramagnetic insulator. Now, here we have a normal case, oxygen band, and D stays split by crystal field on Ag and T2G, but also there is monoclinic distortion, and T2G is split on Eg pi and A1G. That is a result of insulator calculation. So we can obtain and reproduce insulator. But the most interesting story is if we can reproduce metal. And that is the result. Yes, in metal insulator transition, in this material, there is small lattice distortion without losing symmetry. And using lattice parameter for metallic case, we reproduce metal, and for insulator case, we reproduce insulator. And they are in very good agreement with photoemission. Now another vanadate. Another vanadate when we have heavy fermion with lithium vanadium 204. It's very rare occasion when we have typical heavy fermion with effective mass 25, but no F states, because usually heavy fermion materials are F electrons. Yeah. Here we have again partially filled T2G band, but we have 1.5 electrons. And that's our results. Indeed, we have succeeded to reproduce extremely sharp peak just on the Fermi. And here there is a photoemission, and that it did shows that typical heavy fermion transition and a typical heavy fermion behavior. Now, so-called charge transfer insulator. Hubbard model is working with just D band, so let us say with narrow states, narrow bands, and even non-degenerate. For charge transfer insulator, the story is that it's supposed that upper Hubbard band is above oxygen band and lower Hubbard band is below oxygen band. So then oxygen band is between Hubbard bands, and then the first transition is charge transfer, which means from oxygen state to D states. That's our results in DFT calculations. Indeed, we have everything. We have D states here, we have oxygen states here, because they are very strongly hybridized. So the naive picture, so that we have Hubbard bands and oxygen between them, is not true, because sure, D states are strongly hybridized with oxygen states. And here we calculated doped charge transfer insulator. It happens in real material, lithium X, nickel 1 - X. And here, the holes are introduced not by spectroscopy, not photoelectrons, but by doping. And indeed, we have shown that the holes in charge transfer, in doped charge transfer insulator, have predominantly oxygen character, which is important. And that's ARPES and result photo emission spectra in comparison with our calculation. So as you see, you have dispersive band with this oxygen band and non-dispersive band with its D band. Exactly as people have seen experiment. Now, the most interesting story is not modern insulator state, but metal transition from metallic state to insulating state. And it is experimentally seen in transition under pressure in magnesium oxide. So, what happens? First, we see about occupations and atomic states. Yeah? So we start from partially filled T2G and G bands for metallic states. And then when we decrease volume, it is strong redistribution. So EG orbitals become nearly unoccupied, but while T2G mostly occupied. Simultaneously, which is more important, we have transition from high spin state because to low spin state, because in metallic state it is high spin, which means spin 5 halves, the maximum spin, while in metallic state, no, in solid state, in metallic states, it's low spin state. How it happens? So first, we see insulator for both T2G and TG. And then after transition, we have nearly empty EG band and partially filled T2G band. So configuration was T3E2 and in low spin state T5E0. And that's important because when we go from this transition, orbital and spin redistribution, we have huge volume collapse. And that collapse is reproduced in our calculations too. Actually, in this transition is competition between crystal field splitting and exchange energy. When we decrease volume, we increase crystal field splitting, and then delta CF become larger than J, and then we go to low spin state, so we lose magnetic energy, but we gain crystal field energy. Now, pretty interesting story about covalent insulators, iron silicide and iron stibum. That's the story interesting because normally when we have metal transition with correlations induces appearance of the gap, mode gap. While those materials are already insulators or semiconductors with relatively small gap, experimentally with at low temperature and in calculations. And that's it. DFT calculation. As you see, there is a band already without any correlations. What happens when we switch on correlation? It's a pretty strange story, but band gap decreases. So that so correlations decreases band gap, while it should increase. But this gap is band gap. Decreasing the band gap happens due to the band narrowing. So if band width is m star times smaller, then band gap also becomes smaller. And now about magnetic properties. So we see the most interesting story about this iron silicide is that while at low temperature, it's non-magnetic because it's insulator. Then with decreasing temperature, magnetic response increases and then saturates. So it goes from non-magnetic insulator to magnetic metal, bad metal, but nevertheless metal. And that's a result of our calculations of optical conductivity and magnetic susceptibility. Indeed, we see that the first band gap is becoming filled out with increasing temperature, and also susceptibility increases. The reason is that this band gap becomes filled by hoppings due to correlations. So that's the story, that we have transition from insulator to metal with including correlations. Now, pnictide superconductor. That's interesting story that in '86 everybody was excited. No, 86, 2008. Everybody was excited. New high temperature superconductors. Unfortunately, they didn't become really high temperature, still lower than cuprates. But nevertheless, very interesting, and there was a lot of discussion about importance of correlations. First, again, here there are no good separation between D band of iron and P bands of arsenicum. So we could use two types of calculations with Bonnier functions. First, when we have only D band, and then we have strong admixture of P states to D, or we're using full set of bands, and then it will be just D states. Yeah? So that's results for only D bands also, and then we have weakly correlated regime, which means that bands are narrowed, but nothing more interesting happens. But the same results we have when we have full bands calculation with D states and P states also. Also, as you see, bands are narrowed, and we could call it weakly correlated regime. Now, and at last, lattice distortion and correlation. The most typical here is potassium copper fluorine. Experimental is strongly Jahn-Teller distorted materials, so that octahedra here in plane are elongated alternatively on A and B axes, which corresponds to strong orbital ordering. However, in standard calculations, without correlations, Jahn-Teller distortions it doesn't happen. It doesn't give a gain in energy. So that's it. Black line is GGA, but it is one of the version of DFT, density function theory, as a function of Jahn-Teller distortion. You see, there is no minima. But if we include correlation, we have very strong effect and minima very close to experimental one. So that that's important because 20 years ago, in 25 years ago, we did calculations with day plus U and obtained the same results, but that was for a spin ordered case. Here we have it in paramagnetic, so there is no any ordering at all. And the last results is F electron in cerium. Cerium, metallic cerium, has two phases: gamma cerium, low temperature, and alpha cerium at high temperature. Both are FCC, so the isostructural, which is very important. It's a rare case when we have isostructural transitions. And also there is a volume collapse. So we increase low temperature in this gamma phase, and on spectra you actually don't see anything on the Fermi, anything corresponding to F states. But then we increase temperature and volume collapse happens, 15%, a lot. And then complete difference in photoemission and reverse photoemission spectra. We have a lot of these states of the Fermi. And our calculations confirms it, that for gamma states, we have practically nothing in the Fermi, while for alpha states, we have a strong F peak. So conclusions. The Anchorman field theory is a powerful tool to study correlation effects. Ab initio definition of the orbitals is very important, because in normal Hubbard model, it is just some atomic states with some Coulomb interaction strengths, but using linear function formalism and constraint DFT calculation, we could obtain both. We could have explicit form of atomic type orbitals and calculated also Coulomb interaction strengths, so that DFT plus DMFT calculation scheme is also first principle, which means that it has no outside parameters. It's very important. And this method was successful in describing paramagnetic modulator, correlated metals, Cheshire and oscillator, metal transition with pressure, temperature, internal distortion, and so on. Nevertheless, in the end, I should say that it is not omnipotent method, because it's on-site. It takes into account only local correlations, local on-site correlation. And if you need inter-site, non-local correlations, then it cannot do anything at all. The most famous failure is superconductive cuprates, where exactly inter-site Coulomb correlation and fluctuations, spin fluctuation are mostly important. So, unfortunately, this problem is not solved till now. Okay, I'm finished.
Okay, thank you, Vladimir, for a very interesting talk. So we have several questions in the chat. Would you like to read them by yourself, or I can read them?
Just here. Wait a moment. I should switch off demonstrations. Yeah. Oh my God.
You can.
Остановить. Так. Okay. So I am ready for questions.
So, okay, we have first question from the chat, which is, or maybe it would be better if the participant who answers the question will say directly. Would you please, at the same order?
The chat is for offside. Yeah. This question should be on Zoom. Yeah. So anybody is ready? Give me Zoom questions. Chat is separate story. Chat could be done anytime. Just online Zoom conference questions. Anybody?
Yeah, could I ask something? Can you hear me?
Yeah, I'm
Hello?
hearing.
Okay. I asked this question on the chat, but I think I will repeat it. So
Yeah.
what is the current definition of mod insulators in a more general way?
Mod insulator.
Yeah.
Oh, it's very old story. It in 30s. Yeah, everybody was knowing about band insulators. Yeah, but mod introduced the idea of mod insulator where this material become insulating due to the Coulomb interaction, which electrons have on one side. For example, if we have one electron per side, yeah, and hopping between sides is small enough, so we have narrow band. And when two electrons meet on one side, they could not do it because Coulomb energy of repulsion on side is larger than T hopping between side. And Mott proposed call them Mott insulators. That's it.
Yeah, okay. Thank you. But I think the real question here is how do you tell the difference between, so for example, if you take nickel oxide, which is a well-known mod insulator, as far as I know.
No. Nickel oxide is not Mott insulator.
And why not?
Because again, it was proposed by Savatsky, conception of charge transfer insulator. Mott insulator, it means that you have first excitation from D to D, from low Hoover band to upper Hoover band. And then actually your gap is defined by U, Coulomb interaction parameter. Charge transfer insulator and nickel oxide, as an example of that, means that oxygen band is between low and upper Hoover bands. So between unoccupied D band and occupied D band. And that means that first lowest energy transition would be from occupied oxygen band to unoccupied D band. In contrast to Mott insulator, where first excitation is from occupied D states to unoccupied D states. That's it.
Okay, understood. Thank you. And maybe the last part of the question is, so if you have this phase transition, metal insulator transition, and is there
in what material?
I think in the general way right now, is there a way to define an order parameter that you will see change? As in, for example, if we have magnetic transition, right, from paramagnetic to ferromagnetic, we can define a magnetization.
I specifically emphasize in my talk about V2O3 material, because normally there is transition from paramagnetic metal to antiferromagnetic insulator. That could be described by band model. See? If you introduce spin ordering, antiferromagnetic spin ordering, then you could obtain the gap, and that would be a band gap. Yeah?
Right, yeah.
So specifically in V2O3, there is narrow phase diagram region where transition happens from paramagnetic metal to paramagnetic insulator.
Mm-hmm.
Okay?
Yeah.
And that could be done only by DMFT.
Okay, yeah, but it's still a metal insulator transition in a paramagnetic state, right?
Yes.
So
and that could be prescribed only by DMFT, nothing else.
I understand, but is there in the same way as we can define magnetization as an order parameter when we have paramagnetic, ferromagnetic transition or paramagnetic, antiferromagnetic transition, is there a way to define a more general order parameter for metal paramagnetic paramagnetic insulator transition? That was my question, I guess.
There is no order parameter here, because if you have paramagnetic metal, paramagnetic insulator transition, there is no order. See? Order parameter transition means that on one side you have disordering, on the other side ordering. When you have metal transition from paramagnetic metal, paramagnetic insulator, you have no order, and then you have no order parameter. You have no change of symmetry. Symmetry is not breaking.
Okay, thank you.
Yeah.
Can I ask a question about the U calculation? So is the U calculated from the DFT Hamiltonian or the 1 year Hamiltonian?
From DFT. From DFT.
Okay, thank you.
Can I ask one more question?
Constrained DFT. So we apply additional constraint potential, got different energy of any function, different occupancy of a function. But it's DFT, constrained DFT.
Okay, thank you.
Okay, I think we are finished with the question. So thank you again, Vladimir, for your lecture. And let's move to the second talk of our morning session, which is presented by Dmitry Novoselov from the Institute of Metal Physics. So, Dmitry, are you here?
Oh, could you hear me?
Yes, we hear you well. So please share your screen. The floor is yours.
Okay. So, do you see it?
Yes,
okay.
Everything is fine.
Great. Okay, let's start. Good afternoon, dear colleagues. And first of all, I would like to thank the organizers for the opportunity to participate in this workshop. The results that I will talk about today were obtained by joint efforts in exciting work with my colleagues, Dmitry Korotin, Alexey Shorikov, Vladimir Anisimov, and Artem Aganov. And today I will talk about exotic class of materials, electrides. These are the compounds that confine electrons in periodically distributed crystal voids, and such trapped electrons are free from one-side electron-nuclear interaction and can exhibit complex behavior. My speech will contain two parts. The first is a brief introduction to the electrides, and the second is devoted to our investigations of quantum many-body effects arising due to interaction between confined electrons. But before I will start, let me turn to a good old joke. What color is an electron? Actually, we know that the color of an electron is determined by the color of the photon that electron emits when moving with acceleration or when moving from one energy level to another. In fact, this question is related to the topic of my speech. The point is that the concept to explain the properties of electrides historically comes from solvated or dissolved electrons and F or color centers. In early 20th century, Charles Krauss introduced the idea of anionic electrons to explain the solubility of metals in liquid ammonia. In solutions, electrons are free from interactions and are the smallest possible anions. All alkaline metals, alkaline earth, calcium, barium, strontium, and two lantanides, europium and ytterbium, may dissolve in ammonia, and the optical spectra of the resulting solution independent on metal. And these spectra are characterized by a white asymmetric band in the near infrared range. As a result, diluted solutions are blue and paramagnetic and consist of solvated electrons and cations. As the metal concentration increases, the interaction becomes important, and also spin pairing is observed. At sufficiently high concentrations, the solution become metallic and golden color. The attached electrons can be seen not only in the solutions, but also in crystals. There are road deposits of sodium chloride where under irradiation from nearby rocks, free electrons may be located in defects of the crystal lattice, and as a result, such sodium chloride crystals become weak conductivity and such. The first crystalline electrolyte was a cesium crown compound, which firstly synthesized in 1983, and its structure was determined in 1986. In this compound, each electron is trapped in almost spherical empty cavity surrounded by 8 cesium cations. Unfortunately, organic electrolytes are thermally unstable, so which limits their use. But at the same time, with these two works, electrolytes began their journey. Actually, the most clear illustration of electric nature is the first inorganic electrolyte, which is stable at room temperature. It is myelinite. It has ionic framework, contains of calcium, aluminium, and oxygen atoms, and its structure is formed by 12 cages per unit cell. This framework has a positive charge, but inside the cavities there are contour anions oxygen 2-, and these contour anions provide electroneutrality in the mineral in total. But oxygens can move through the openings connecting the cages, and also can be removed from the mineral as a neutral oxygen molecule, and left to access electrons in the crystal, which convert as a result myelinite to an electrolyte. The resulting electrons also can migrate through the crystal, and by hopping to the neighboring cage. Electrolytes actually have a numerous applications in practice, and due to the fact that anionic electrons are not bound to nuclei, they are relatively too diffuse, which leading to a high conductivity and relatively easy to extract them, which provides also low work functions. Such properties allow for almost ideal applications to various technologies, including superconductors, electron emitters, optics, lamps, battery anodes, radioactive waste storages, catalysts for the range of applications, including ammonia production, organic synthesis, CO2 splitting, and electrons in electrolytes are, on the one hand, the simplest anions. But on the other hand, due to their low mass and rising quantum effect, they can participate in more complex interactions with each other and with cations. As a result, such interactions give rise to many body effects, which mean to have an impact on physical properties. We try in our work, we try to find and describe the phenomena in electrolytes which cannot be explained within independent particle approximations and go beyond for directly account the correlations between anionic electrons. For this purpose, we are looking for and evaluate science which is typically related with correlations, and we have studied the three electrodes. First, it is elemental calcium with a complex phase diagram, and especially interesting simple cubic phase, which realized under pressure, and it inaccessible with single particle approximation. And in the next system, it's first layered 2D electrolyte, with a large enhancement of effective electron mass. And finally, the beta phase of ytterbium-5 antimony 3 compound. This is a 0D electrolyte with exceptional high localized magnetic moments at normal conditions and interesting mode-insulating features. Generally, our goals is to understand how strong and how important be correlations between electrolyte electrons and how they affect the physical properties of electrolytes. On the way to finding the questions, the answers on our questions, we use the DFT plus DMFT approach. Vladimir Ilyich has just described this method in detail, so I will myself to mention only the main points, some references without any formula. So to get the non-interacting band structure, we carried out DFT calculations with pseudo-potential packages, quantum espresso or best. And then comes the crucial step, which need to obtain an analytical description of the electrolyte states and to get the maximally localized Wannier function basis, including the electrolyte states centered in the crystal voids. For this purpose, we used Wannier 90 package. This pack also used to extract the non-interacting Hamiltonian in real space. And in the last step, finally, we to take into account Coulomb correlations, temperature effects, and many body effects for the constructed Hamiltonian, we use DMFT. The effective DMFT quantum impurity problem was solved by continuous time quantum Monte Carlo algorithm as realized in AMULET code from our lab. So let's turn to the first system. It's metallic calcium, and this system attracts considerable interest because of the unexpectedly complex phase diagram. Besides, it has the highest critical temperature of superconductivity among elements under pressure and equal about 25 Kelvin. The phase diagram of calcium was studied both experimentally and theoretically, and the X-ray experiments showed that at low temperature, calcium undergoes a series of phase transitions, as we can see on the left figure. At the same time, how it was shown by Artem Aganov with authors, DFT is unable to reproduce the simple cubic structure as a ground state of elemental calcium at any pressures, despite the fact that at the experimentally phase diagram, there is a vast area of stability of this phase. Another interesting point about calcium is the formation of electrolyte states under pressure. This idea was proposed by Artem Aganov with authors and was based on analysis distribution of the valence electron localization function. In this case, the maximums of ELF located not only on the calcium sites, but also in the voids between them. Overlap of the valence and core orbitals lead to expulsion of the valence electrons to the voids between at the center of the cells. And another interesting point that it was shown in the simple cubic phase, the resistance has an unusual behavior under pressure, and this behavior associated with unusual electronic properties arising from the S to D electron transfer. Assuming all these facts, and to shed some light on the relationship between structure changes, electride formation, and Coulomb correlations between these electrons, we investigated several phases of by using the DFT plus DMFT method. So we started with the DFT calculations, and this slide it is shown the valence charge density distribution for simple cubic and beta thin phases. And we can see that a simple cubic structure has a pronounced charge density maximum in the middle of the unit cell. And the Baker analysis revealed that this area contains about 0.67 electrons. Another interesting point that beta thin phase is a one-dimensional electride with narrow serpent-like 1D channels along C direction. To obtain the analytical description of the electride states, we used one-year function projection procedure. And to reflect the idea of electrides, we started with 6 one-year functions, 5 one-year functions with D symmetry centered on calcium sites, and 1 with S symmetry centered in the middle of the unit cell. At this slide, we can see the spatial distribution of S symmetry one-year function in blue color, and 2 one-year functions with D symmetry in yellow. Also here, one can see the contribution of one-year functions with this symmetry to the band structure. And as we can see, the lowest almost quite types of one-year functions with S and D symmetry, and which is strongly hybridized with each other. So all the 6 one-year considered to be correlated, and result in the DMFT impurity problem has the dimension 6 by 6. Before we have started to DMFT calculations, we calculated the Coulomb just told, and we have obtained the value of U equal 0.47 eV, and then we use this value for all the phases under investigation. This value is smaller than the typical for transition metals, which equal 2, 3, and up to 10 eV for nickel or copper, but calculated on atomic local orbitals. In this case, it can be explained with effective screening by more effective screening by one-year functions, which has more spread on the nearest sites. Then we evaluate the DMFT calculations for all structures, for 3 structures, simple cubic, beta thin, and the CMMM, for several values of the volumes of unit cell to simulate the different external pressures. The band structure of a simple cubic phase, as shown on the left figure, has significant differences in comparison with DFT. And this behavior is expected for such small value of U. At the same time, DMFT give us the total energy correction arising from correlation effects. The obtained values of the energies are almost independent on the applied pressure for all the structures. So then we use this correction to calculate the total energies, and we substituted the resulting total energies into the third order Birch-Meinhof equation of state for all crystal structures and calculate the enthalpy for each phase. On this slide, we can see the enthalpies of beta-tin, CMM, and CMMM phases compared to the simple cubic one, which is shown by zero line, and calculated by three methods: DFT, DFT plus U, and DFT plus DMFT. In agreement with previous calculations, the enthalpy of a simple cubic phase calculated using DFT is always higher than the enthalpies of a beta-tin phase, while the enthalpy for CMMM structure lies between them. DFT plus U method also did not reproduce the phase transitions. Eventually, our calculations showed that when dynamical correlations are taken into account, the experimentally established sequence of phase transitions occur, even with small value of U. So it allows us to conclude that the weak Coulomb correlations are strong enough to reproduce the chord sequence of the phases. Okay, the next system is dicalcium nitride. It is the first discovered two-dimensional electride with anti-cadmium chloride structure and with one excess electron per formula unit. The anionic electrons in the calcium nitride confined in the interlayer voids between the calcium layers. And at this slide, we can see the isosurfaces of electron localization function with different values. And there are actually several reasons to study the interactions between interlayer electrons in this system. First, under pressure, the system undergoes a series of phase structural transitions accompanied the lowering of dimension of electride voids from 2D, then 1D, and finally 0D. And these transitions are also accompanied by a metal to insulator transition under pressure, which closely associated with a change in the degree of localization. So also the quadratic temperature dependence of the resistivity is observed up to 120 Kelvin, indicating that the electron interaction is much stronger than electron-phone interaction. And the last interesting point at the right bottom figure, here we can see the magnetic resistance, which observed on the magnetic field. If magnetic field perpendicular to the 001 plane of the crystal has a negative sign. Whereas on the in-plane field, the magnetic resistance conventionally parabolic and positive. So such behavior arising mainly from electron-electron interactions in 2D system. Besides, the experimental data demonstrate a large enhancement of the effective electron mass to about 2.5, and these estimations were obtained from Julie Lawrence model and determination of the plasma frequency, as well as the method. There is a method to analyze the Fermi surface as a function of magnetic field orientation. Additionally, in the experimental work, it was shown that the results of DFT calculations do not correctly describe the position of the energy bands obtained in the ARTAS. Those available data indicate that dicalcium nitride can behave as correlated material. And it is interesting and important to understand how such Coulomb correlations affect the physical properties of this system. The band structure calculations show that the single band which cross the Fermi level consists mainly of non-atomic electronic state centered right between calcium layers with small distributions of neighboring calcium and nitrogen atoms. This indicates that the electrical conductivity and transport properties of the calcium nitride is due to electrons enclosed in the space between the layers. So to describe such electronic state, we construct 4 maximally localized linear functions. The first linear function represents the electric state and has the symmetry of s orbital, and its contribution to the band structure is shown in yellow on the left figure. So the other 3 functions have the symmetry of p orbitals and centered on the nitrogen atoms and describe the fully occupied bands. The non-interacting Hamiltonian was constructed in this basis and then solved in the framework of the MFT for several values of U parameter. And this slide presented the dependencies of self-energies on Matsubara frequencies, also the green functions on the imaginary time in the inset. The value of Green's function at half of beta, at tau equal half of beta, indicates that character of conductivity, metallic character of conductivity at intermediate values of U, and some tendency to transition to the semi-metallic state if U equal 4 eV. At this value of U, self-energy function tends to diverge at 0, which indicating a sharp increase in localization of electric states. Then we obtain the analytical continuation of self-energy dependencies and calculate the spectral functions. And as we can see from the figure on this slide, for small value of U equal 1 eV, spectral function of electrolyte state resemble the density of state obtained using DFT. Okay. An increase of U up to 2.5 eV leads to renormalization of the spectra. There is a narrowing of the band around the Fermi level, and the low and Hubble bands appear, and denoted by the blue arrows. A further increase of U up to 3.5 eV, and hence the formation of the quasi-particle peak and upper and lower Hubble bands. At the same time, at U equal 4 eV, the transition to the semi-metallic state is accomplished. Next one. The dynamic Coulomb correlations. The dynamic Coulomb correlations lead to a rise in the renormalization and renormalization of the band structure and the shift of the Fermi level, which depends on U and temperature. And to analyze this, we have calculated the electron mass enhancement as a derivative of the real part of self-energy on the real frequencies at 0 frequency. And it is important that at U equal 2.5 eV, the electron mass enhancement equal to 0.35, which agrees better with experimental value. We also have estimated the upper band of the U parameter using more localized basis of atomic orbitals by the linear response approach. And we have obtained the U equal to 2.78 eV. But the resulting effective U on the maximally localized linear function should have slight smaller due to more effective screening. To analyze the effect of correlations on the band structure and compare it with experimental APIs, we evaluated the energy dispersion along two different directions in the Brillouin zone. A comparison of the FT bands and the APIs from the MFT leads us to conclude that the interaction between layered anionic electrons result in a smearing and shift of the electret band down relatively to the Fermi level, and whereas the nitrogen bands shifted up. The study of magnetic properties, we started with analysis of local spin-spin correlation function on the imagery time that characterize the lifetime of the local moment. And if the moment is localized, this correlator equal square of S, and such behavior is typically for strongly correlated compounds. And in decalcium nitride, this behavior was observed at U equal 4 eV. On the other hand, at small values of U, it indicates the delocalization of spin moments. At the U equal 2.5, at which the mass enhancement is the closest agreement with experiment, and this case corresponds to an intermediate correlation strength. Also, we calculated the local spin susceptibility as shown here, and its behavior for different values of U reinforced the conclusion that at U equal to 2.5 eV, there is a partially localized and relatively large magnetic moments are presented in the interstitial site. Also, here presented the spin correlation function calculated for different temperatures with different beta values. And it showed the increase in localization degree when temperature increased or better decrease. And finally, we have calculated the uniform magnetic susceptibility for different values of U. We have done these calculations by applying a small external field to our Hamiltonian and then measuring the magnetization. The uniform susceptibility at U equal 4 eV strictly follows the Curie's law and have a negative sign of Curie's temperature, and this fact indicating the presence of antiferromagnetic fluctuations. The dependence obtained for U equal 2.5 had the same behavior in the high temperature region, but it exhibits a rapid drop below 500 Kelvin and some plateau up to 1200 Kelvins. And the localization degree at this U is low, and we do not imply the presence any long-range magnetic order, but just only the antiferromagnetic fluctuations. At U equal 1 eV, he has a small drop at low temperature, but it is almost constant at high temperature. Obtained result means that correlation effects between anionic electrons result in such the complex behavior of the magnetic subsystem of decalcium nitride. And the last system I would like to talk, this is a dimorphic ytterbium-5 stibium-3 compound, which can crystallize in alpha or beta phase with hexagonal orthorhombic structure correspondingly. In both cases, the system contains ytterbium atoms with 2+ valence and 1 excess electron per formula unit. But in alpha phase, the interstitial space has a quasi one-dimensionality and formed by ytterbium 6 octahedral chains along C-axis direction. At the same time, the beta phase of ytterbium 5 stibium 3 contains the confined anionic electrons in ytterbium 4 tetrahedra, and this is the phase is a zero-dimensional electride. The interstitial states of this compound are partially filled, but despite this, the system demonstrates the semiconducting type of conductivity and Curie type temperature dependence of magnetic susceptibility. The authors of this experimental work cited here suggest that such behavior allow to create these compounds as a strongly correlated material, and electrons of electrides could have the strong interaction between them. Also, they have shown that DFT-based methods, including DFT plus U, fall to describe the band structure and, of course, paramagnetic phase of this compound. Experimentally, there are the energy gap about half of EV in the beta phase. So it's of interest to understand the role of Coulomb correlations between electride electrons, information of such interesting properties. We use the same method, DFT plus DMFT, to analyze. And as I already said, the beta phase has anionic electrons localized in periodically distributed tetrahedral voids, and the corresponding energy bands is crossing the Fermi level. And at this slide, we can see the we construct 4 maximally localized Fourier functions, and here is shown the spatial distribution one of this function and the contribution of all 4 Fourier functions shown in the band structure in red color. It is important that actually the electride Fourier functions effectively contain the contribution from the states of ytterbium atoms formed this tetrahedra, as well as it is quite important, the essential part from the nearby antimony atoms located right between this tetrahedra. So these contributions are due to hybridization between electride states and 5p antimony states. And this situation provides some indirect interaction channel between the electrons localized in the cavities of neighboring tetrahedra. So the obtained basis of the Fourier functions were used to construct the Hamiltonian, and which are then solved within DMFT, also for several values of U. As we can see in the inset on the figure, in the inset of the figure, the Green's function at tau equal half of beta indicates the evolution of the system from metallic to insulating character with growth in U, and self energies diverged. Has a tendency to diverge in zero. So to analyze the evolution of the electric bands through this metal insulator transition, we relate the spectral functions, and as we can see at this slide, in the absence of electronic correlations, the electric states form the peak right on the Fermi level. Then for small value of U equal half EV, a 3-peak structure beings to form with a central quasi-particle peak at the Fermi, as well as the upper and lower Haber bands, which is typically for moderate correlations. These bands denoted by the blue arrows. Then an increase in U up to 0.75 eV leads to disappearance of quasi-particle peak at the Fermi and enhancement of the well-pronounced Haber bands. The further growth of U up to 1.5 eV is accompanied by forming the semi-metallic state with gradual decrease of the density at the Fermi. And at U more than 1.5 eV, the energy gap gradually opens and the transition to the strongly correlated multi-insulator state occur. At the U equal 2 eV, the value of energy gap is quite close to the experimental one. It's about half of eV. These results demonstrate that the multi-insulator state in this system exists due to the Coulomb correlations between the electrons located in the crystal voids. The next step was varying the electronic temperature by changing the beta parameter at the fixed value of U equal 2 eV. And in this way, we obtained the set of green functions shown at the figure for one impurity. The rest are qualitatively indistinguishable. And as we can see here, the decrease in temperature leads to enhance an insulator nature of the Green's functions, which is typically for semiconductors. So we can conclude that in agreement with this observation with the experiment means that semiconducting behavior of the beta phase of this compound also caused by Coulomb interactions between electrolyte electrons. Then to study the magnetic properties of this system, we also analyzed the lifetime of the local moments by evaluating the corresponding correlation function. Actually, the least correlator depends on the imaginary time, the more localized magnetic moments becomes. And the behavior which is typical for highly correlated system with strong localized magnetic moments was observed already at U more than 1.5 eV. At the U equal 2 eV, each electrolyte density acts as a magnetic centers with highly localized magnetic moments equal 1 Bohr magneton. And finally, to analyze the contribution of electrolyte subsystem to the magnetic response on the external magnetic field, we calculated the temperature dependence of uniform susceptibility. As we can see this slide, all the dependencies of He with different U values strictly follows the Curie-Weiss law. And the dependence of He at U equal 2 have the best agreement with experimental dependence denoted by violet circles. So another interesting point that the Curie-Weiss temperature estimated from extrapolated inverse He has a negative sign for considered values of U, which indicate the presence of antiferromagnetic fluctuations. And we suggest that these fluctuations arising from antiferromagnetic interactions, which has super exchange nature and occur through the 5p orbitals antimony atoms oriented right on the faces of neighboring tetrahedra. And finally, the model mainly derived from the interstitial electronic states properly describes the magnetic features of beta phase of ytterbium 5 antimony 3 with moderate values of U parameter. So let me briefly resume the main conclusion of my speech. And firstly, exotic state of electrons confined to the interstices can be correlated, and these correlations maybe with different regimes from weak to strong. Secondly, the correlations on the electric states can represent an essential part of the physics and quite interesting properties how listed here. And if we use the right way to describe these confined states and properly taking into account the Coulomb correlations, Coulomb interactions between excess electrons, we can catch manifold of properties arising due to many-body effects. I'm finished. Thank you for your attention.
Thank you, Dmitry, for your
I'm ready to answer your questions.
Yeah, so now we have time for several questions. So I see one question from Sergei Streltsov, please.
Okay, thanks a lot, Dima. Thanks a lot for nice presentation. I really enjoyed it. Actually, I have a lot of questions, but let me probably ask two of them. So first of all, what is everyone can, not everyone, but we can at least do band structure calculation and plot. If we are smart enough, then we plot charge density and have a look whether there is a charge density inside some voids, right? And then we can understand that this is an electrolyte, right? But what are the experimental evidences? So what are, say, smoking gun experiment that you have a substance and you see some behavior, and what would be the experiment which would show you experimentally that this is an electrolyte? So this is the first question.
Yeah.
Let me probably just ask both of them, and then you will answer. So the second question is about, so if I understood correctly, all your electrolytes are S-like. So the charge density is more or less spherical. Is it possible to have p electrolytes and then to have orbital degeneracy and all effects which would arise from such things? So do we know anything about p electrolytes? You know what I mean?
Yeah, I understand your questions, but in our study, on the second your question, in our study, we have never seen electrolytes with different than S symmetry orbitals, unfortunately. And the first your question about experiment, it is a quite difficult question actually, because there is just experiments that could give us some information about charge density, X-ray and something like this. And no other experiments I have no.
I mean, some anomalous, say, resistivity dependence on temperature, some strange optics.
It's a common property. It's not related with actual electrolytes.
No
like
smoking gun experiment. No,
No.
smoking gun evidence. Okay, good. Thanks.
Thank you.
Okay, I think those questions which are in the chat, Dmitry can answer during the other sessions, because we are a little bit behind of the schedule. So next session should be started at 11:45. So if you don't mind, let's have a break, for example, 10 minutes, and after 10 minutes we can start. Vladislav, is it okay for you?
No, unfortunately, because I have one more, let's say, event at 2 o'clock. So for me, it's better to start right now, probably.
Okay, okay. I think it is better to listen to Vladislav now, then have a small break and listen to the second presenter of the session. Okay. So now we have a talk by Vladislav Blatov from Samara Center for Theoretical Material Science. And so, please.
Thank you very much. And also thanks for the invitation of me to this school. Actually, I counted, this is my 6th USPEX school, because I participated in this school since 2013. And I was in China, in Italy, in Russia, but this is my first USPEX school in, let's say, virtual space. A good experience. Thanks. So I will start my let's say, okay, my presentation. And this is a special topic on using topological models in searching for new crystal structures. And in some way, these models can supplement DFT models and USPEX algorithms. We have some experience in this field already, but these are some new, let's say, achievements in this field. I will present first some general information about topological description of crystal structures as nets. Then we will consider some topological relations using subnet and supernet concepts. And then the new network topological model of configuration space that helps us to find new structures. Some methods of search for atomic configurations in solids using this model, and software and databases which can be used for this purpose, and some examples of application of this method. First, words about topological description of crystal structures. You know this very simple model which is used in crystal chemistry when we represent the structure as a periodic network with atoms and bones. And this is a bit, let's say, another model compared to typical physical model when we consider atomic nuclei and electron density around them. We can use this simple model also to algorithmize some standard operations for solid state transformations, and also to describe the structure with a simple set of numerical parameters. And these numerical parameters which characterize the topology, the connectivity of the structure, can be stored in databases. And now we have some special software which can create such databases, and then using these indices here, I present some typical set of such indices for types of topological indices, which characterize the crystal structure up to isomorphism. And using these numbers, we can directly determine the topological type of the structure. And for this purpose, we use also our collection of topological types, which now includes more than 200,000 entries. Even more now, because we included many hypothetical structures, more than 500,000 hypothetical structures were added recently to this database. And to designate topology, we use some topological nomenclatures. One of such nomenclatures is shown here. This is our CSR, 3-letter codes. Using these codes, you can easily describe topological types shortly. An important background of the topological model is the subnet supernet concept. Actually, we can easily obtain subnet from some supernet by just breaking edges in this subnet. For example, if we have this initial topology, primitive cubic topology, we can break some bones like this here and get another very well-known topology, cadmium sulfate topology here. But this is, of course, not the only way to break the bones. We can do it in another way and get, for example, this twofold interpenetrated arrays when we have two different, two actually topologically equivalent, but anyway different networks, which do not, which are not connected to each other, but interpenetrate to each other. For example, the third way gives us some low-dimensional structures from high-dimensional. So we have many methods to break bonds, and the question is, can we enumerate all of them? Within some restrictions, for example, if we restrict the topological complexity of the resulting networks, we can do it by strict algorithms. And this is actually what our software does also. Then using these relations between supernets and subnets, we can construct a so-called net relation graph that shows us these relations. And for example, if we have here this set of nets, and for example, B1, B2, and B3 nets are supernets with high connectivity, then we can break some bonds in them and produce from them some new nets, which are subnets in this case. And this is the net relation graph that shows us the relations between supernets and subnets. Then using this graph, we can find some important features of this system. For example, we can see that starting from some net, we can get many other nets. And if we take any pair of nets within the graph, we can find all possible ways of transformations of these nets by breaking bonds or creating new ones. So this is a way to enumerate possible topological transformations of the structure. Next point is that we can compute topological distance between these vertices, nets in the graph. For example, this net B4 has distance 1 to all other 4 nets in this part of the graph. This means that it can be transformed into these nets in one step by breaking just one kind of bond. But for example, the net B5 cannot be obtained from B4 because there are no topological ways between them, and the distance is formally infinite. So in this case, this graph consists of two isolated parts, and the corresponding networks are topologically independent. Now we can, for example, find also topologically fastest transformations between these nets. Again, for example, net B4 can be transformed to B7 in this way, but also in this way, the red one, which is the shortest one, of course, in this case. So we can expect that this way could be at least topologically favorable, most favorable. Now, one simple example for transition between diamond and Lonsdaleite structures. Here you see that one of possible topological ways of transformations of this structure structures is the intermediate 5-coordinated supernet, the transition state. And we can see here that if we break red bonds in diamond, this is just one kind of bond, the red bonds, then we create new yellow bonds in the transition state, we get finally Lonsdaleite. So diamond can be transformed to Lonsdaleite by breaking just one kind of bond and then creating one kind of new bonds. The transition state is still 3-dimensional, so this system does not require graphitization, passing from, for example, graphite subnet. Now let's consider the general concept of the network topological model. We have, for example, some configuration space with 4 different phases, A, B, C, and D. There are infinite number of geometrical configurations in this space, but we have just 4 different topological regions. This means that topologically we have just 4 points in this space, 4 different topologies. Although these topologies can be geometrically distorted, of course, but for our analysis it's not important, because we can work with abstract nets without their geometrical embedding. And this means that for this system, we just need to consider 4 points instead of infinite number. Of course, these boundaries between the regions can be complex, like this, like shown in this inset. And some intermediate topologies can exist in these regions. But anyway, the number of these topologies is limited. And we have here actually 4 so-called stable network regions and some metastable regions between them. And these metastable regions can be considered as topologically considered as supernets or subnets of the stable networks. And this also means that we can find possible transition pathways between known phases and also find new phases if needed. For example, let's phase B is diamond, and let phase A be Lonsdaleite. So this line, this pathway between them, topologically corresponds to the picture that I showed you before, and these intermediate phases can be, for example, 5 coordinated supernets. But what are the phases C and D here? We don't know, and probably these are new phases. For this purpose, to answer this question, we should find transition pathways to these phases from, let's say, Lonsdaleite or diamond, by again breaking or creating new bonds in them, and finally finding new intermediate states here. And we can scan in this way rather large, or probably even the whole rather large part, or even the whole configuration space, and enumerate all phases in this, all topologically different phases in this space. So importantly, the number of these phases is countable instead of a number of geometrical configurations. And this is also a way to study reconstructive phase transitions and single crystal to single crystal transformations and some solid state reactions, etc., etc. But these are simple structures. Diamond and Lonsdaleite are just monatomic structures. What to do with complex structures? For example, organic structures or metal organic coordination compounds, complex ionic, etc., etc. For this purpose, we can use the so-called underlying net concept when we simplify the complex structure and reduce it to some simple underlying net. An example I show you here is very well-known metal organic framework, one of actually the first metal organic framework synthesized in practice, MOF5. And this is the complete framework. This is the same for comparison. Then we find here the structural units, which are actually tetrahedral zinc complexes connected by organic links. And we consider these complexes and these links as the whole. We replace them with their centers of mass. And finally, after such simplification, we get the underlying topology, which is just primitive cubic topology. Then we can consider topological transformations of this topology into other topologies. And these transformations will mimic the transformations of the complete structure. To construct the underlying net, we can use some strict simplification algorithms, which finally allow us to simplify quite different structures with different structural units, like, for example, atoms, organic or inorganic complex units, ligands, links, etc. And also metal clusters, polynuclear complex groups. For example, here in these three quite different fragments, we get the same topological fragment, simplified topological fragment. So probably these structures will be transformed in the same way, which will correspond to transformations of the underlying topology. And with this method, we can find relations, topological relations between quite different structures. Here, an example with two microporous structures is shown. This is on the left, this is sodalite, very well known zeolite, and on the right, the so-called ZIF, zinc imidazolite framework. They are different, of course, chemically, completely different, but topologically they are the same, actually. If we consider these fragments of in these two structures as the same fragment, we replace these imidazole ligands with their centers, which correspond to oxygen atoms in sodalite. We get the same sodalite underlying net. And after constructing underlying net, we can use the decoration operation to construct from this simple net some complex nets, complicated structures. Different methods of decoration give us different structures from the same initial topology. Also, of course, we can use this technique to consider structural transformations between complex structures. One more important point when we're looking for relations, topological relations between complex structures is the local proximity of these structures, local, again, topological proximity. For example, we can consider, we can look in the databases for the structures which are locally similar to diamond structure. For this purpose, we can construct a rather large fragment of the diamond structure, like shown here, 41, for example, fragment for 41 atom fragment. This is the diamond structure, also a piece of diamond structure, and this is a fragment inside this structure. Okay, but then we can consider quite another topology like this, for example, more complicated, topologically more complicated than diamond. But anyway, this topology, this network contains these fragments, which are completely topologically the same. So we can say that this topology is locally quite similar to diamond, although if we consider the overall structure, it's different, of course. This search for final fragments inside the infinite structures is very powerful, and it for example, helps us to find the fragments which are responsible for topochemical reactions like these, or supramolecular synthons, which again correspond to some special methods of connecting structural units together. And this is also a way to find some typical supramolecular architectures in complex compounds. This is quite unique possibility. For example, it is also useful for metals and intermetallic structures when you can find clusters, some metal clusters inside the bulky structure, inside the three-dimensional network. For this purpose, to perform the topological analysis, we use software which we developed since actually 1989, during last 30 years. This is Topos Pro, and you can download this software for free at our website, topospro.com. And also now we started the project for online service, which performs some operations realized in Topos also. And this is TopCrest service. And with this service, you can use your CIF file and just drop this CIF file into this window, into this service. And you, after some time, you will get a complete topological analysis of your structure. For example, here, we can see the calcite, and this service gives you two possible ways of topological consideration of this structure. When we consider atoms, carbon, calcium, and oxygen atoms as structural units, so when we consider the structure as a whole, or when we separate structural units more complicated, like carbonate ions and calcium atoms. And in this case, we have simpler topology. In this case, you see this is just PCU primitive cubic topology, like, for example, in MOF5, the same topology. So you can easily find all representations, all topological representations for your structure, and also find the possible topological relations with other structures. But for this purpose, you need to use topological databases. We produce a lot of different databases. I mentioned here just two our topological collections. The first collection is a so-called TTD collection, Topos Topological Databases. As I said already, it contains now hundreds of thousands of topologies, more than 6 actually, 100,000 now, including hypothetical structures. And all these data are arranged into in the Topos software, in the local version, and also in our online services. In TopCrest, you can also find another set of collections. This is TTO collection, which shows us where these topologies are observed, in which structures. And now we have more than 2 million observations of these structures in real crystals or in some model structures. And again, in Topos Pro, you can use this user interface and find the occurrences of the topologies and also the lists of the structures where these topologies are observed. And you can also use our online service, TopCrest. In TopCrest, after you, for example, determine the topology of your structure, you can immediately get the list of structures which have the same topology, and at least find first if your topology is new or not, and which structures have the same topologies. Probably these structures are quite similar to your structure. And directly from this service, you can go to Cambridge Structural Database or an Organic Crystal Structure Database and see what is this structure, how it is constructed, etc., etc. So here all these services are integrated together. Now some more examples of application of all these methods and tools. And here again, see a simple example. This is the methods of how to get diamond and Lonsdaleite structures from graphite structure. We have graphite in the center, and the question is which atoms should be connected to each other to get diamond structure or the Lonsdaleite structure. And the topological methods immediately give you this information, so you can see how the structure should be organized to get one topology or another topology. This is again diamond and Lonsdaleite, my old example, because they can be transformed to each other not through graphite, but also through three-dimensional structure without losing dimensionality. Okay, now more complicated example, actually two examples. Here we have two pairs, tridymite and keatite. These are two silica polymorphs. Tridymite is high temperature polymorph, but at normal pressure. Keatite is high pressure polymorph. The same concerns ice, hexagonal ice, normal ice, let's say, and ice 3, which is high pressure phase of ice. Both these pairs, I mean tridymite and hexagonal ice, and also keatite and ice 3, have the same topology. This is Lonsdaleite topology, tridymite and ice hexagonal, and keatite and ice 3 has the keatite topology, some special topology, which is called keatite. And the question again, how to transform tridymite to keatite and vice versa, and also these two phases of ice. And here a possible topological way is shown when we, again, you see break yellow bones in the ice structure, in the hexagonal ice structure, then create new bones, red bones between water molecules. And finally, after relaxation, we get the structure of ice 3. This is quite complicated, actually, topologically complicated transformation. You see that the corresponding supernet is topologically quite complex. There are different nodes with different coordination in this supernet. And this transformation being quite complicated is of course hindered strongly, and it's quite it's actually impossible to get directly tridymite keatite from tridymite. There is no experimental way to find it, at least At the moment, it's not, it's unknown. Keatite can be obtained only from the melt by applying pressure. Between ice structures, this transition is possible, but at special conditions, and it's again not typical, let's say. It's very hindered anyway. So topological transformation also shows us the complexity of the transition. And this is energy profile for this transition for tridimide keatite. And you see here that there are many intermediate states here, many metastable topologies between these two structures. Again, it shows us how complicated is this transition. Another example, this is again two modifications of ice hexagonal and ice 2. Ice 2 can be obtained from hexagonal ice easily under pressure. Indeed, in this case, topological transition is quite simple. We have just one transition state between these two phases. But you see that the distances between the molecules, water molecules that should be connected to each other in a new phase in ice 2 is sometimes quite long. But anyway, from topological point of view, we need to break these yellow bones in ice hexagonal, then relax the structure, then form these new red bones, and finally get this right structure on the right. This is ice 2, and this is the intermediate supernet, the net before relaxation, the net after relaxation, which corresponds to the final structure. Another example concerns the structures which don't need the transformations, actually, which don't need the intermediate structure, intermediate topology. In this case, one topology can be transformed to another topology just by breaking bones or by creating new bones. No need to pass through the transition, topological transition state. For example, this typical transition, which occurs in some substances under high pressure, from zinc blende type to rock salt type, can be topologically described simply by breaking these red contacts in the initial rock salt structure, and the resulting network, although still geometrically similar to rock salt, but topologically it is already zinc blende. And after this, after some relaxation, you will get zinc blende. Vice versa, if we have geometrical configuration for zinc blende and the bones typical for zinc blende, but we create these new links, red links, the resulting topology will be equivalent to rock salt. And again, after relaxation, we will get rock salt as a result. So here there is no topological intermediate phase. Now, more about generating new crystal structures. Again, I talked already about graphite and obtaining diamond and lonsdaleite from graphite, but of course we can consider other ways of linking of graphite layers together, keeping typical four-fold connectivity for carbon atoms. And we will get new structures, new topologies. And these are new topologies which were not observed before. After relaxation, we get not bad structures with just 0.4 electron volt above diamond energy. And importantly, these structures are quite hard, close to diamond by hardness also. And in our recent study, not published yet, but submitted now, we generated many new carbon allotropes using the scheme in some way similar to evolutionary algorithms, but using the topological criteria for generation. So we started with some 6 initial structures, 6 initial carbon structures, known structures, and actually we selected them randomly. There were no, for example, diamond or lonsdaleite among these structures, but we were interested if we get diamond and lonsdaleite as offsprings of these parents. And we actually performed 3 steps. At each step, we generated some topological relatives using supernet subnet relations of the initial structures, and find at the first step 34 offsprings, topological offsprings. Then we select from these offsprings low energy structures, less than 0.2 electron volts compared to diamond, and created the next generation, the next set of parents, 5 new parents. From these parents, we generated another set of offsprings and repeated this procedure again. And at the third step, we obtained no parents, no low energy parents more. And finally, with all these steps, we get in total 224 new carbon allotropes. Among these allotropes, there are structures also close to diamond by energy, and also even one structure which are harder, a bit harder than diamond, but which has higher energy than diamond anyway. The details of this study will be, I hope, published soon. Okay, so if we consider all this scheme as a whole, the general algorithm is the following one. First, we consider some known structures which can be taken from different databases, like databases of real structures, real compounds, inorganic crystal structure database, Cambridge structural database, PDF database. Then we simplify them if needed to get simple underlying nets. Then we consider subnet, supernet relations between them and build the net relation graph for the resulting underlying net. And using again supernet subnet relations, we can find topological transformations to get new phases from these known topologies. And if needed, these new phases can be then decorated with some complex structural units to get complicated structures. As a result, we can explore in detail the topological space instead of geometrical configuration space. And as I said already, for this purpose, we don't need to consider infinite number of configurations. Of course, these methods can be and should be, of course, combined with DFT approaches, and we did it already partially. also with Atom within USPEX, when USPEX already can use some initial topological structures. But of course, we need also DFT at each step of topological generation to check the stability of the structures and their properties, etc., etc. But the topological methods can help can help us to speed up the generation of the new structures, the method of to find the offsprings from the initial set of parent structures. So all these methods are united within our Topos Pro software, also, as I said, in the local version and in partially, at least partially, in our online service. And in the end, I would like to thank my group in Samara Center for Theoretical Material Science, and also Russian Science Foundation for support, and you for your attention. Thank you.
Thank you, Vladislav, for this great talk. Actually, do we have questions? Okay, I think we have no question. Okay, thank you again. And to save some time, we will move to the fourth speaker of our session, who is Vladimir Baturin from Skoltech. So, Vladimir, please.
Yes, I'm ready. Okay, do you hear me well?
Yes.
Okay, I'll start sharing my screen. Sorry. Sorry, my computer doesn't want to share the screen normally. So do you see my presentation full screen?
No, we see only you.
Okay, 1 second. And now?
Yes, now we can see you.
So thank you, Sasha, for the introduction. My presentation will be about the prediction of clusters using USPEX, prediction of structures of non-clusters using USPEX, and I will show a couple of examples of application of this technique to silicon-oxygen clusters and the search for new charge traps in cadmium-selenium clusters. So I will start with the description of the standard technique, the 000 technique. And before doing that, I will say a couple of words on prediction of cluster structure in general. So unlike the crystals, where there are, for example, practically important materials where we have 2 or 3 or up to 10 atoms in the unit cell, in case of clusters, the clusters which consist only of 2 atoms are irrelevant for practice, so those are just dimers. And when we considering the solid state, due to periodicity, we can like take into account only those couple or 3 atoms that are in unit cell. But in case of nanoclusters, it is not the case. So although they are small, we have to consider all of their atoms. So that means that in general, the problem of cluster structure prediction is much more computationally demanding. The second thing is also, unlike the crystals, clusters are very often have very low symmetry, so the symmetrical like tricks and approaches don't work. Neither do the considerations like cutting from the bulk, etc., because we have a very large share of surface atoms. And at last, but not the least, the experimental data about the nanocluster structure is very scarce. So very often we need to rely only on the computational data. So let's start with the very beginning of how the algorithm works. So now I will present the regular 000 method. As you remember probably from yesterday's practical session, all of the modes of working in USPEX, they are decoded by 3 digits. So first digit is the dimensionality. The second digit is whether we consider the molecular system, and the third digit means that we consider either the fixed composition where we put 0, or the variable composition where we put 1. So the variable composition for crystals will be highlighted in today's tutorial, but here we look at 000. So it means that we look at the clusters non-molecular with fixed composition. So we start our initialization with randomly picking one of 32 crystal point group and one of important non-crystallographic point groups. Actually, there are infinite number of important non-crystallographic point groups, but we choose only the most important ones. You can see that there is a lot of number 5s in here, which means that those are a variation of 5-fold symmetry, which is forbidden in crystals, but appears quite oftenly in case of crystals. So now that we initialize the first generation, we apply the variational operators. So like in the whole ideology of the USPEX algorithm, the most important one is heredity. And the heredity here is modified, of course, because in case of crystals, we have the so-called zebra heredity, where we choose slabs of 2 different parent structures, and then we like alternating these slabs. In here, we use the cut and splice mechanisms when we choose half from one parent and half from other parents, and then we splice them together to form an offspring structure, which you can see here on the bottom of the slide. We also slightly change the fingerprint vector. Fingerprint, let me remind you, is the vector that allows us to determine whether we already seen this structure before, so we don't need to consider it again, or this is a new structure. So we compare 2 fingerprints, and by this means we identified like the identity of this structure. It's kind of a passport of this structure. And also in the USPEX code, we use the most oftenly we use VASP, which is solid state code. And in this case, the crystals should be put as an input to this file. So some periodical system, but of course, clusters are non-periodical systems, so we have to somehow trick VASP to consider our clusters, although they are not periodical. To do this, we use the supercell approach, where we formally made the crystal, but this crystal consists of these empty boxes, where we have in the center very like small clusters, well, small compared to the size of the cell. What aim do we pursue by this means? we achieve that we formally have crystal, but the periodical replicas of our clusters do not or negligibly interact with each other. So they are like far from each other. And you see from, I think it will be tomorrow, from the tutorial dedicated to the clusters, that there is one important parameter called vacuum size. So you need to specify which distance between the periodical replica should be considered in VASP calculation. Okay, but for practical application, we usually need to determine the structures of not only for one fixed composition, but for some range of composition. This is due to the many reasons. Among them, the most important is that in experiments, you don't always have only one composition. For example, when you shoot the laser, shoot some sample with the laser, and then you evaporate the clusters, those clusters are for sure not don't have the same size. They have some, as I said, the distribution of sizes. Also, when we study the nucleation processes, we also need to consider the range of sizes or compositions. And finally, if we are aimed to find some clusters with desired composition, we need to screen also number of compositions. So usually this task is, this problem is solved by the consecutive computation of different compositions, but we introduced the new approach, which is somehow relevant to the variable composition for crystals, which will be tackled in today's tutorial, the so-called variable cluster structure prediction, variable composition cluster structure prediction. So in this case, we specify not the single composition, but the range of composition. For example, here you see the chunk of input file. So we specify the atom type, which is copper and gold. And here you see the ranges of numbers of copper and ranges of numbers of gold. So from 6 to 10 for copper and from 6 to 10 to gold. Also, we need to modify the fitness function. So fitness function is the parameter that we minimize or optimize in general. In case of fixed composition, it's just the energy. Maybe it's some kind of thermodynamic potential, but anyway, this is some form of energy. But here energy doesn't work because it doesn't make sense to compare the energies of species with different compositions. So this new notion of fitness is based on the concept of magic clusters. So what is magic clusters? Here on the left panel, you can see the energies of optimal Lennard-Jones clusters, which is obviously computational result. And on the right, it is actual mass spectra of lead N clusters. And both on the left and on the right panel, you can see some peculiarities in this graph. So here you see on this, the graph is generally rather smooth, but there are some humps on Lennard-Jones 7, 13, 19, etc. And on the right, there are also some compositions which have like very prominent peak in abundances, which physically means that we have some increased stability. Before we describe this increased stability, I need to make a remark that in case of clusters, there is no point considering the absolute stability because all of the clusters are essentially unstable. Every cluster wants to be a crystal because the relative number of surface atom is minimized in that way. So all of the stability criteria will be relative or local. So in our case, we chose the second order derivative of energy with respect to the number of atoms, or to be more precise, the second order finite difference. So here you see the same system, but for this system, we calculated not the binding energy itself, but this second order derivative, which is defined as you can see here on the bottom of the slide. So the criteria for the cluster to be stable is the positive value of the second order difference, which is the sum of energies of its neighbors minus twice its own energy. Or we can reformulate it as following. So the energy should be less than half sum of the neighbor's energies. That means physically, if you consider the gas of such clusters, like floating in the vacuum, so we take the pair of these clusters, identical, and if it is energetically favorable for them to exchange one atom, then those clusters are non-magic. So there is a channel of like decay or decomposition or like recomposition, I don't know. So again, if the second derivative is positive, then the cluster considered magic. And finally, the construction of fitness is shown on the graph here. So we here on the vertical axis, you see energy per atom. On the horizontal axis is the number of atoms. And here what we do is we connect all of our lowest energy magical clusters. And if we want to define fitness for some particular clusters, we calculate the distance between energy distance between this cluster and this segment line here. We also, besides the updating of our fitness function, we also need to introduce new operators. Well, part of the variational operators are the same as in case of fixed composition, but there are some very important new operators that do not conserve the composition, but they're very effective. And by the way, I forgot to say that the basic idea of this variable composition is that, okay, I will go back a little. So usually people do separate calculation for different composition, but now we unite all of this composition in one calculation. Why did we do this? Because very often, if we have close composition, then the structure is also very similar. So there is no point in like recalculating this structure from scratch. We have, for example, structure for silicon 10, then it is quite highly probable, highly likely that structure of silicon 11 will be very much alike. So we introduced new operators such as transmutation. It is like we can randomly change the identity of some atoms. For example, if our cluster consists of two chemically very similar elements, then we can switch, for example, copper to gold or vice versa. We introduced new heredity, which is similar to the heredity that I already described, but it doesn't preserve the composition. And also what I was talking about is add or remove atoms. So we take the cluster and from some stochastical considerations, we add some atom or remove an atom. So in more detail, it looks like this. 1 second. So the probability of atom to be removed depends on its coordination number. This coordination number is defined like here. It is slightly like generalized coordination number. So this atom will be more likely to be removed, this oxygen, than this one, because it has lower coordination. And when we want to add atoms, an oxygen atom to silicon, we will most likely choose this silicon atom because it has the lowest coordination. Okay, here are the tests. We compared the separate calculation with our one-shot variable composition calculation, and those tests, they showed the speed up to 50 times. So from 5 to 50, depending on the type of system that we considered. For example, here, this is what we have, the energy that we have from 200 calculations. This is after 1,500 and so on and so forth. So this is like process of the convergence with respect to the number of ab initio calculations. And on the right, you can see the same process, but for the variable composition calculation. So the speed up is quite evident. Okay, so the first example is silicon-oxygen clusters, which we published a year ago. So this system, from practical point of view, it is important for astrophysics because the silicates are formed from silicon monoxide molecules in circumstellar space. It is important in experiments in growth of nanowires. And also we considered the biological impact of small silicon-oxygen nanoclusters. But from the computational point of view, the system is very interesting because usually the structures of clusters are much more diverse than the structures of corresponding bulk materials. But in case of silica, only silica itself, silicon-oxygen-2, has 14 structural forms with only one stoichiometry. So probably in case of clusters, the diversity will be like unimaginable. Okay, so this is like the net table for what we got. We varied number of silicon from 1 to 15 and number of oxygen from 0 to 20. And you can see here the in this table, the white cell is what we reproduced. The asterisks are the were predicted for the first time, and this plus signs are the structures that we've improved using our method. The criteria of stability was updated for the case of binary systems. This generalization is very straightforward. And here you can see this map of stability that Artyom showed in his first presentation yesterday. So the blue is kind of the sea of instability. You can see here two mount ridges. First of all is, of course, the silica ridge, the silicon-oxygen-2, which we're all familiar with. The second one is, curiously, the silicon N oxygen M, where silicon to oxygen ratio is 2 to 3. And also some isolated islands of stability. And the last slide on this topic is I will show you some particular examples for each ridge. So you can see here silicon 8, oxygen 16. This ridge of 2 to 3 ratio is usually obtained from the silica, but with removal of this doubly bounded oxygen on the surface. Well, surface here is a far-fetched term because all atoms are on the surface here. And as for the islands of stability, those are either segregated clusters where pure silicon is attached to either silica or 2 to 3 ratio clusters. And also there are some particular points enriched by oxygen where they exist due to high elevated symmetry. Okay, that's it for silicon oxygen, and our recent paper that got just published is the charge traps in cadmium selenium clusters. So the clusters are very good candidates, actually perfect candidates for light emitting devices because their wavelength depends only on the size. However, they are pretty unstable first, and the second is that there are such phenomena as charge trapping. So there are states on which when electron falls on that state, it stays there. Usually those states are on the surface, but we may say for sure that those states are very much localized. So when we are dealing with charge trapping, we need to deal with localization. So formally, the localization is defined using the participation ratio, which is defined by this formula. In the denominator, we have this sum of contribution of particle atom to some ith molecular orbital. So this participation are usually taken using the Malakin populational analysis. So here, for example, I draw the very simple model molecule where the wave function is equally distributed over these three atoms. So this wave function has coefficients 1 to square root of 3, 1 square root of 3, and 1 over square root of 3 here, and here it is 0. So the participation ratio here is 3, and this value, we will use this value as the number of atoms on which the state is localized, or it will be denoted as n log. So this state is indeed localized on 3 atoms only. So here is the net result. Sorry for the layout here. I don't know why it is showing like this, but I think it is quite clear. So here we use the n over n log, so this ratio. So the higher the value here, the more localized traps is observed on this in this very cluster. So for example, we see here this peak over here. This is cadmium 10, oxygen 15. So we have on the highest occupied molecular orbital, we have there a very high localization. So what conclusions can we make from this picture of 4 near gap states? So yes, we see here highest occupied molecular orbital, lowest unoccupied molecular orbital, and 1 state below and above. So first of all, we see that these traps are much more abundant in this lower right triangle. That means that that traps are mostly observed in selenium-rich clusters. So the traps are mostly localized on selenium, which actually was known before, but here we actually proposed before, but here we confirm it. The second thing is that we have some like areas. We see that these maps are rather smooth, so there are areas where the traps mostly absent. That means that again, this confirms the theory that the close composition leads to the close structures, and then that means that they also have close properties. So what else can we see from this from these maps is that the most clusters are trap-free. It is contrary to the general belief that, actually not belief, but the general notion that unpassivated clusters should have traps. However, they are trap-free due to this so-called self-healing effect. So if what usually people did is that they cut the clusters from the bulk. So that led to a lot of dangling bonds, and the dangling bonds are usually the trapping states. They correspond to the trapping states. But actually, due to the stabilization, these dangling bonds, they saturate. So here you see 3 steps of stabilization. So we first cut a structure from bulk structure, cut the cluster from bulk structure, then we allow it to relax. And then we compare the relaxed structure to the global optimized structure. And we see this consecutive lowering of energy and the clearing of the gap here. So we have here kind of intra-gap state, the metalloid, I don't know, metal-like spectrum. And after the optimization, we have a very nice dielectric spectrum. So here is this 2 examples of stoichiometric clusters. So as for classification of the traps, we singled out three major types. First of all is mostly due to the pi bonding or pz orbitals situated at selenium atoms. The second type corresponds to this sigma anti-bonding orbitals, also on the selenium atoms. And the third type, which is quite seldom occurred, but it is quite peculiar, is the cadmium atom, which is caged inside the cadmium-selenium framework. So this is like the descriptive part, and also we studied the mechanisms, the new mechanism, because before we have only one mechanism which is described in 2017, I guess, article, this p orbital and the selenium. But then we discovered new mechanisms which are due to the large difference of sigma and p bonding. If two states have a very big energy difference, then they're spatially isolated one from each other. Okay, I will jump to the conclusions. So here you see the summary. You see this like joint map of 4 different states around the gap, and the abundance of traps of different types. So the most widespread traps were found in a very unbiased way. So we didn't construct any traps as it was done before. So usually people like had some idea how traps may look like, and then they introduced these traps up to their guesses into the bulk cut crystals. But here we did everything using the structure prediction, so absolutely unbiasedly. And we explained 2 new mechanisms of charge trapping. Okay, so that's probably it, and I am ready to questions.
Thank you, Vladimir, for your presentation. So if anybody have questions, actually we have one question from the chat. If you can read it and answer.
When we discuss about clusters, especially the small ones, it is important to include also the total number of valence electrons. For example, aluminum 13, fortunately, is more stable. Actually, this is more of a comment than a question. Yes, indeed, we need to include this into consideration. It is actually very close to the, it is called shell model or jelly model of clusters. So there are, like in the atoms, there is a notion of electronic shell. And when this shell is filled up, so this cluster is more stable due to the number of valence electrons indeed. I'm just wondering, what is the advantage of using supercell and VASP rather than using molecular approach? Well, from my experience, the periodical codes are much more robust because, for example, I use Gaussian to refine my results using hybrid functionals. And for example, Gaussian is, well, generally, first, it is slower, and also it is very picky about the geometry. So you need to like always keep an eye on this Gaussian calculations, unlike VASP. It is because of this very universal nature of plane wave basis. Yes, superatom model. How the molecule charges vary with the vacuum distance. with the vacuum, I don't quite understand the question. With the vacuum distance, molecule charges. You see, all of the final results were obtained. So we first predict the structures in using VASP, and then I recalculate everything in Gaussian. So in that latter case, the vacuum is infinite. Maybe I missed out. How? Sorry. Maybe I missed out. Could you explain how do you verify stability with respect to possible polymerization of clusters? Actually, polymerization is one of the channels for the clusters to change their compositions, and the number of these channels is infinite. So we chose only one channel from the infinite ones, the one that is just described by the second order derivatives, because as for polymerization, we would have to first polymerize these clusters and then see how the energy changes. And we cannot afford it, because if you have two clusters each of 40 atoms, then you will have to consider this 80 atom clusters, which is quite an expensive thing to do. The clusters in the book and the vacuum needed. Yes. Question about resources. How long take the prediction of all silicon oxygen clusters? Well, it took about 3 months, I guess. In large clusters, the question of electronic configuration signal interpret is crucial. How do you treat this problem? We did this. We varied the multiplicity in Gaussian in case of silicon oxygen clusters. And we found that in quite numerous cases, the triplet is like more stable than the singlet.
Okay, does anybody have more questions? Okay, if not, then let's thank all the speakers, and so then we have a break until 2:45. After that, we will start our third session of the day with one lecture and tutorial. Okay, thank you all.
Thank you. So, hello everyone. The next speaker is Alexander Shapeyev, and his lecture is Machine Learning and Interatomic Potentials.
Thanks for introduction. I hope you can hear me. If you don't, please say.
Yes, we hear you well.
Okay, let me share my screen. Okay, can you see the presentation mode now, Sergey?
Yes, yes.
Okay. So let me make the controls of Zoom easier. So thanks for joining. I'll be talking about machine learning interatomic potentials, and I did not list all the collaborators for the work that I'm gonna tell, but a lot of this is done with my group, and later in applications, I'll show you who this was done with. My background is in mathematics. So until I became an assistant professor in Caltech, I was doing basically mathematics. And now I'm applying machine learning to regression of interatomic potentials. And I'm rather interested in the technology of the interatomic potentials, how to do them, but rather how they behave and what do they do and why they don't work and so on. This is why this is important. So this is a typical pie chart of total supercomputing time spent on different things. And density functional theory is the #1 consumer of supercomputing time. So, and then together with classical molecular modeling and quantum chemistry, this makes it a total of 40% of supercomputing time spent on this. So any algorithmic improvement here would make high impact on the field. One motivation of what I'm doing is the following. So first, more and more materials properties can be computed with DFT. And one of my favorite examples is this, where a group of authors, so led by Jörg Neugebauer and Blažej Grabovski, they computed very accurately the melting point of aluminum. So they had like 128 atoms and 8 to 8K point mesh, and they did a extrapolation with respect to number of atoms and very lengthy calculations. So they found that the GGA is about 880 Kelvin, LDA is 970. Experimental value is somewhere in between. And all of this, they do it automatically with the software that they develop. So it's called Pyrant. So they develop this automated simulation protocols that in the end give you the melting point and probably even together with some uncertainty. So the trend is that the DFT calculations can be automated and more properties can be computed. And more interest is to compute other properties. So here I'll be presenting machine learning potentials. And the way I'm thinking about this, I want them to be part of such automated calculation protocols. So my favorite problem is just to illustrate how this perform is automated construction of convex hulls of stable structures. So this is the part of American Materials Genome Initiative, FLOLib library. And they have maybe thousands of different phase binary and ternary phase diagrams. I call them zero temperature phase diagrams. And so they obtain them in an automated way with DFT. So the way they're doing the scheme is here. so they have a fixed number, a few hundred to a couple of thousand crystal structure prototypes that they relax on quantum mechanics. And the only difference between what they're doing and what USPEX is doing is that in USPEX, there's more advanced structure sampling, right? Otherwise, I mean, I say the only difference because I'm interested in machine learning this, right? So to me, I'm sitting at the bottom here and I'm looking up. And so to me, the difference is here, right? But otherwise, so there's a crystal structure prototype, it's relaxed, its energy hits a point on the concentration versus energy plot, and you take the lower convex hull, and these are the stable structures. And the basic question that I'm trying to answer is, can this be machine learned? If yes, then you can accelerate quite a bit this kind of calculations. So next, I'll be talking about how I understand machine learning interatomic potentials. So I like to think of this method of constructing potentials as a data-driven and multidimensional interpolation. So if you imagine you have a water molecule and you're trying to construct a potential, what you can do is you can parameterize it with 3 degrees of freedom, and then you take a reference quantum mechanical model, and you can just compute the values on the grid and do any kind of spline interpolation, for example, and you're done. You have the potential energy surface. The problem is when the number of atoms is large. You can only, number of atoms is 100. It's hard to do a 300-dimensional interpolation. So what you do is this: you split the energy into contributions of different atomic environments, and you assume that they are local. So each contribution is local, and this is the way you incorporate locality. And then the function V is already something that can be regressed with modern and even classical fitting or machine learning methods. So I'll probably skip this, but this is just to say that, like traditional interatomic potentials, they also have this form, but instead they are assuming a particular functional form for this contribution of the environment. And there are not too many fitting parameters here, and they're fitted to a few quantum mechanical calculations or even experimental data. So instead, machine learning potentials, what you do is you choose a very flexible functional form. It can be neural networks. I'm using polynomials, but you don't limit the the expressive power of your functional form. Then you generate lots of data, compute the energies, compute the quantum mechanical forces, and then you want to minimize the difference between your model that you're trying to develop and the quantum mechanical model on data. There's one catch in this scheme, and namely sometimes sampling the configuration is a part of a problem. So if we go back to this problem of constructing the convex hull, your problem is to find these structures on or near the convex hull. And if you're trying to solve it with machine learning potentials, then you need a potential energy surface for your interaction to be able to equilibrate those structures. And to have a machine learned potential energy surface, you first need to sample the training set. The training set should be relevant to the structures. And this is almost exactly the problem you have started with. So usually it's the most time-consuming part of doing machine learning potentials, and we do it by active learning. So what we actually do is, there's a molecular simulation. It can be molecular dynamics, it could be relaxation, and it could be USPEX-driven relaxation, for example. And then we get a configuration, and we need to return the energy and gradients for this configuration. So instead of just predicting, we first answer the question, does this configuration needs learning? If yes, we generate the quantum mechanical data and retrain our potential. But otherwise, if no, we just directly predict the energies and forces. That's it. Now a few slides on the 2 components. So this is component number 2, prediction of forces and stresses. for the energies and its gradients. Then the active learning, this is the first part of the pipeline, and then I'll be showing you different applications. Right, moment tensor potentials. In a couple of slides is this. So when you develop a new machine learning potential, you need to describe the environments. You need to develop the descriptors of the environments, and we use this formula that we call moment tensor descriptors. So we're sitting on the central atom I, and we sum over all the neighbors, and so it's split in the radial part and angular part. Now, if you, for the moment, forget about the angular part and look here, this is just a simple radial function. And you can interpret it as the different radial function may concentrate on different atoms, like different shells of atoms at different distance from the central atom. And these are good descriptors, but that's not enough to describe the environments in a unique way. So what you do then is you consider the angular part. So without the angular part, it's just a kind of a weight of the shell. With angular, if you just multiply by r, by this vector between atom I and atom J, then it will be this kind of center of mass. It will be to what extent the mass is shifted from the central atom. If you take the product of two, it will be eccentricity and so on. So they're tensor value descriptors. And now if you take different contractions of this tensors to a scalar, there's a way to enumerate it. You can get an expansion of your potential. And then it depends on you, the environment of the atom, and parameters theta, which are linear expansion parameters that you find from data. So this is roughly what you do. This is something I want to skip. This is something I want to show. So Ivan Kruglov also showed this figure that I like very much. So the MTPs have a pretty favorable balance between computational cost and error. So all the potentials, they actually reach a good few millieV per atom error. MTP can do it a little faster, half of the order of magnitude or one order of magnitude faster. So I was very happy with this, but I realized something which I show you later, which I tell you later after. No, actually, it's a good slide to show you this. So reliability is another issue, right? So the previous graph, it showed computational efficiency, it showed accuracy. But then there's one more aspect, which is reliability. And this is very important. So here in this test, I take a path between two different phases. It's a pathway between two equilibrium structures. This is the transition structure, transition point structure, and then DFT predicts, so these structures, they roughly have the energy of -4. The transition structure have the energy of 2. That's what DFT predicts. But then MTP predicts the energy of -10 to the power 5. And this MTP, the way we do it is it was not trained on this on this structures. So instead, we just trained it on this structure. We trained it on this structure. If it did not see the structure, the answer is completely unreliable. And what we're doing is we're calculating extrapolation grade, which I'm going to show you in a minute, so we can actually predict. So the red, it's by the extent by which we extrapolate. So at the end, we don't extrapolate. Here we do extrapolate. And if we add these structures to the training set, then MTP would work very nicely. And this is our answer to the reliability problem. It's active learning. It's detection when we extrapolate and adding those to the training set. The way I'd like to illustrate this is a better example. It's a more illustrative example, one-dimensional. So I imagine that my blue curve is a true quantum mechanical potential energy surface. And you can see that the linear approximation is doing not so good in interpolation, but extrapolation is not as bad as the fifth order polynomial, right? And the machine learned potentials, they're more close to this fifth order polynomial. They have hundreds of parameters, and it's very easy to overfit with those. So the way the active learning works, if we can detect when to switch on learning, then the first 6 points will be learned exactly. And then we keep adding points such that we always keep 6 points on the curve. Then the points are added. The next point will be added here. And then the algorithm will decide, no, let's keep this point. It's already pretty well covered here. And it will continue until there will be extrapolation. And then learning will be switched on again until the whole region will be nicely covered. I'll probably skip this. One short, tiny image on how this is done. So it's important to do it without getting quantum mechanical data, right? It's actually an algorithm to decide when to compute it. So a pictorial view is this. You can think of basis functions as atomic descriptors, and every configuration would be a point on this atomic descriptor space. And we take a convex hull, and the convex hull, we say it's an active set. And if the point is inside the convex hull, then we say it's an interpolation. If the point is outside, we say it's an extrapolation, and this point would be added to the training set. Now, a question which I'm often asked is this: what if the point is inside, but still far away from any point of the convex hull? So this indeed can happen in many dimensions. But the thing is, our model is linear. And if you start thinking about this, it's not a convex hull, it's actually a simplex that is built on these points. And then this kind of is automatically taken care of. So there won't be such simulation if you start drawing the right picture with simplices and linear models. Okay, that was 15 minutes only. And we're about to show how it works on application. So the first application is molecular dynamics. I call it application 0, so it's a prototypical application. So I take 100 lithium atoms, I run molecular dynamics, and I see how many quantum mechanical calculations I make. So if I run the ab initio MD, it's a black line. I do one calculation per time step. If I do this with active learning, then what happens in the initial trajectory, I do learning pretty often, but then it starts to kind of do it more and more rarely. And somewhere between 500 and 1000 iteration would be a good balance between accuracy and the number of DFT calculations. Now, this is controlled by the threshold, and this is the degree of extrapolation. So if we go back to this picture, we allow a little bit of extrapolation outside the convex hull. And it's typically okay. You can save like quite a bit of time compared to no extrapolation at all, but the error is not too much. So a good value is somewhere between 1 and 10 for the extrapolation, and then compared to no extrapolation, the error is almost the same. And with no extrapolation, there's still error because we start by fixing the number of basis functions. This is 100 basis functions for this lithium system. All right, so back to my favorite application, the convex hull. So this aluminum nickel titanium convex hull is built on 1,500 crystal prototypes that we relax on DFT. And we want to machine learn this, and we do it with active learning, machine learning potential. And now we start with 400,000 crystal prototypes. We calibrate them with machine learning potentials, and we learn on the fly. And this is how it works. So we relax these structures by collecting the structures we extrapolate on, And until all the structures are relaxed, until there's no extrapolation, this is the root mean square error. It's quite large, but still it's less than 10%. It's something like 4% compared to the deepest energy in the convex hull. And we use less than 100 DFT structures. So you should imagine out of this 400,000 structures, sorry, less than 1,000. So less than 1% of the structures were actually computed on DFT. But then 100% of the structures were relaxed without any errors. And we could stop here. But instead, we can just take the 4 sigma interval. We can just take all the structures which are above the computed convex hull by 100 millieV per atom and repeat the procedure. Sorry, it should be not 40 by 60K. So the second time it's 60K pre-relaxed structures. And when we relax them, our error is much better. It's 9 millieV per atom. And then the 4 sigma interval will contain 7,000 structures. All of them can be relaxed on DFT as the final step. As we do it, we find some nickel-rich new structures, at least as DFT predicted, and they were not on the A-flow convex hull because that is limited. To just a few structures, and by taking more structures, we could do that. And what else is important to say? Yes, so on another system, we find some topologically different structures on the convex hull. And so these kind of strange structures, you would not be able to predict with machine learning potentials normally because you would not add those to the training set when you did not know them. So if you want to discover them, you need active learning to detect them and then compute energy when you do this. Right, so if you do these 3 steps, there would be no approximation error in the answer, right? So the only thing we're paying with is the risk of missing a structure in the 4 sigma interval in the screening process. And if we're actually okay with the 9 millieV error per atom, then it would be actually much faster. So with this, it's 100-fold speed up, and the final relaxation take 90%. So that's what I was saying. If you remove the final relaxation, do everything with machine learning potentials, you will have an error of 9 millieV per atom, and the speed up will be by a factor of 1,000. And still, the training set is 90% of the remaining time. So in this particular application, actually speed is not important. In some other applications, it is. But our potential could be 10 times more expensive, and still everything would work almost just as nice. And now when I present this, I say that now the sampling is not the bottleneck, and we can do it with many more samples. And we indeed did that with Artem Oganov, that he showed this graph of different boron allotropes. And I was pretty happy that our potentials worked very well in this. I'll skip this because Artem talked about this earlier. Thermodynamic integration, another thing that was discussed yesterday. And we actually did it for a high entropy alloy. So we did it for a 5-component system. We managed to learn it with machine learned potential. And the task was to compute a free energy at like almost melting point, close to melting point of the structure. And we did it with thermodynamic integration because unharmonicity was important. And so this is more or less 30 millieV per atom is the contribution of unharmonicity. And the state of the art before machine learned potentials was to fit an EAM to a single structure and then compute the reference energy of an EAM, and then do a final thermodynamic integration to find the difference between the EAM and DFT. And if you do that, you would spend about 4,000 CPU hours to get the energy difference. It's an energy difference of 13 millieV per atom. Now with MTP, it's actually 10 times less. It's a 10-fold increase, and MTP can be fitted automatically. So to feed an EEM potentials, we spent weeks of actually manually fitting those potentials to one single structure of this alloy. And this feature of automated training is, as I said, it's important if you want to develop those complex automated computational protocols to later screen many materials and find the best ones. Right, so another thing, we applied another algorithm, not the thermodynamic integration, but the nested sampling. And we found the phase composition and temperature phase diagram of silver palladium in almost automated way. And in a way, we did it so the dotted lines is the experimental, what do you call it, solidus liquidus gap. And the algorithm can actually find those. So those angles on the lines, they correspond to actually onset of phase transitions. And this is something we managed to get. The numbering changed, I did it. So another project we did with a group of Igor Abrikosov, it's actually an accepted manuscript. So they were very much into the business of computing high temperature elastic constants. And we did it about several hundred times faster by doing MTP. And basically we trade about actually a few GPA statistical error. It's something about 5 GPA statistical error to 1 GPA model error of MTP and more than 100-fold speed up. That's the gain in this application. Another cool thing we did with our collaborator from Germany who was stuck in Russia early this year because of coronavirus, and he was very productive, and I think he did several works, and this is my favorite out of those that he did. So it's actually heat conductivity, heat transfer in the graphene borofin 2D structures and across the grain boundaries. So what we did, we computed with DFT, we trained the machine learned potentials, and with machine learned potentials, we computed the heat conductivity and heat conductance of the grain boundaries, and later we did the finite element simulation of those. So this is how we computed, we tested it with BTE transport, but we did the non-equilibrium molecular dynamics method of computing the heat conductance. Computed it for a bunch of grain boundaries of different orientation, computed it for pure borofan and graphene, and then we did the finite element simulation of those. And then we see some interesting patterns in the way that the heat conductivity works, including some anomalous behavior when you kind of add a more, so I think, let me not comment on this anomalous behavior, I don't want to lose time. Now, another application we did with Max Hodab from my group is we ran big simulations of motion of a dislocation. So all simulation before the DFT part, so the simulation was actually done on a few hundred atoms, or at least the potentials were trained on a few hundred of atoms, but now we want to do this with a motion of dislocation. And the way we do it, we actually have an automated procedure of cutting out a small simulation patch on which we want to train also automatically, and then plug it, like taking it, completing it to periodic boundary conditions, and collect the training set out of those and repeat the simulation. So this is something that we did. Another work we did, there are many authors, including experimentalists. Alexander Kvashnin, who already spoke and will also give a tutorial, is also collaborating with us on this. It's an even more challenging application of simulating nano-indentation from first principles. So the algorithm would also detect different environments here and then collect the training set and continue this whole nano-indentation simulation until it reaches the end. And then this is the coolest graph that we got. So these experimental values and theoretical values, they differ by about a factor of 2. But if we kind of calibrate these values to the diamond, so we take the kind of relative hardness to the diamond, then we have a pretty good agreement of a wide range of materials. Okay, few more works and then I'm done. We can do it also for the on-lattice models, although we do not have the code to do it that we can share. So for everything before the dislocations and the nano-indentation, we have a code, and I'll give tutorial on this, how to do it. All of this can actually be reproduced relatively easily. So this is something we're still working on, making a code public. And we don't make it public because we don't want to be ashamed when you start looking at the code. But otherwise, so it's a competitor to cluster expansions. You can treat those on-lattice models in a similar way. You can decompose the energy of a configuration into a sum of contributions of local environments. And if you do that, it works very well. It's just like cluster expansion, but it works on many component systems, which were problems for cluster expansion. So we took this 4-component alloy and we qualitatively reproduced the existing results with the generalized perturbation method, except that this method does not allow for local lattice relaxation. And if we allow for local lattice relaxation, if you look at this figure and I flip the slide, the figure will be completely different. So what we found, if you put the right physics in, what you see is that the random phase for this alloy, it's stable almost down to the room temperature. You will never see phase decomposition in experiment, and it's true, you don't see it in experiment. The phase, no matter how long you anneal, and now we know. So if these results are right, you need to anneal at the room temperature. That's impossible. So we can get this pretty well, and no method before existed. We did the same for vanadium, cobalt, nickel. I'll try to finish fast too. I already see there are some questions in the chat. I haven't read them, but so I'll just finish here on this application. So for vanadium, cobalt, nickel, we repeated the same thing. We included local lattice relaxations is actually responsible for making this alloy random, because if you don't do it, actually the disordering phase transition happens after the melting point. And we had mixed feelings. We predicted the right structure after the phase transition. As you decrease temperature, how it orders. So it forms this vanadium lattice, vanadium sublattice. And in fact, when we predicted it, there were no experimental papers, but as we were kind of investigating, their experimental papers appeared that predicted these phases. So in a way, we made a true prediction without potentials. This is my last slide. So all the code, all we did except for those large scale nano-indentations kind of simulations and on lattice is available. This is the public version. You need to register. So I want you, if you want to do go through the tutorial today, I want you to go through there, click download, and then register for the use of the code. You need to agree not to distribute it and not to use it for commercial purposes. And then you can repeat the steps during the tutorial. Otherwise, you would just see how it's done. So it has a bunch of interfaces, it has active learning, and yes, I think this is my last slide. I thank you for your attention, and I'd be happy to take questions. So Sergey, should I start by reading questions?
Yes, thank you, Alexander. So there are a lot of questions. Could you read them?
Sure. Nice session, Alexander. Thank you. Are there any factors that the extrapolation is dependent upon? I mean, extrapolation is a pure geometric criterion, right? So this extrapolation grade is a function of atomic positions in the environment and the chemical species. So in a way, these are the factors that it depends upon. Maybe I didn't understand the question, so if not, then maybe you can type a more detailed question if I didn't answer it yet. Hongbing Zhang asks, can the accuracy of machine learning to atomic potential be good enough to relax crystal structures? Yes, it was probably in the beginning of my talk, so no, it was done. I mean, I showed it, right? So yes, it's one of my favorite applications is to relax. Lucas Francisco asks, I'd like to ask, how does the active learning algorithm knows when to do the learning? It seems that you need to perform the QM calculation to determine how accurate machine learning potentials is every time. No. So yes, true. It seems that you need that. And this is exactly the problem that you need to solve when you're doing active learning. So active learning, it reduces to an algorithm of some kind of an estimating what is the error of quantum mechanical calculation if you were to compute it. So active learning does exactly, you can say it does exactly the opposite, or you can say it solves exactly this problem. It gives you an estimate on the error without computing the quantum mechanical calculation. And it does it on a pure geometric way. Tao Fan asks, could you explain more about how MTP include unharmonicity interaction for thermal conductivity application? Yeah, so MTP, it's an arbitrary functional form, right? So I can prove, I didn't show you those details, but I can prove that it can learn any local interatomic interaction to any accuracy if you can increase the number of basis functions and if you can increase the cutoff radius. So if your DFT includes unharmonicity and you learn on DFT and your functional form is not limited by anything, it's systematically improvable, then you automatically include unharmonicity.
May I ask?
Go ahead, yes.
I'm Tao Fan. Yeah. So you mean if we want to learn to include the harmonicity in MTP, we need to do the third order first constant calculation, because only such a calculation can include harmonicity interaction.
No. So you do a molecular dynamic simulations and you compute forces. Yeah. And you train on those forces.
Yeah, but
and they include unharmonicity.
Yeah, but if it include unharmonicity, it depends on the potential you used. If your potential didn't include the unharmonicity, or not accurate, how it can reflect.
Okay, so there are two answers, right? Simplified answer is that MTP includes unharmonicity. A less simple answer is to say that when you're talking about unharmonicity or not, you are assuming a certain expansion of energy. You are assuming a Taylor expansion of the energy around equilibrium, right?
Yes.
Then zeroth order term will give you the energy. First order term, so first gradients will be zero because forces at equilibrium are zero. Then second will be harmonic terms and the third will be unharmonic. And that's not how MTP does it. MTP does not assume an expansion around equilibrium. So there's, I mean.
Oh, okay. So
I mean, imagine like a fourth order polynomial, right? It has a third order term and the fourth order term, they're not, I mean, they're not harmonic. And then you just fit it. You take 10 points and then you feed this with some function, right? It will include unharmonicity, although you did not explicitly include it. This is how it's done in MTP.
Oh, okay. Understand. Thank you.
Okay, Hongbing John asks, for the vanadium cobalt nickel alloys, would the short range magnetic ordering be an issue? or in general, the magnetic interaction in completion with interatomic the magnetic interaction in competition with interatomic forces? So this is a very, very good question. And we are actually finalizing the paper. So soon there will be a thing called magnetic MTP. Only 4 people for now know about this, maybe a bit more. We also discussed it with Xavier Gonza. I don't know if he's in the audience now, but it's a very exciting direction. So we treat magnetism as a part of degrees of freedom. So we see the potential as a function of atomic positions and magnetic moments. This is how it's done. And for specifically vanadium, cobalt, nickel, magnetism is not an issue. And this is why they are in a particular magnetic state always. So roughly speaking, very roughly speaking, they're always in ferromagnetic state. And at least we assume, and we get decent results. And if there's only one magnetic state, we can learn it. If there are many magnetic states, where in the case of paramagnetism or antiferromagnetism, then it becomes an issue that needs to be solved. But soon we'll have tools for that. Adam Carlson asks, dear Alexander, how is MTP framework in comparison to cluster expansion, considering obtaining the convex Hull plots? So MTP is, take it as a joke, it's much better than cluster expansion. And the reason is because cluster expansion cannot consider significant relaxations. So cluster expansion assumes that you fix the number of, you fix a small set of underlying crystal lattices. So you can pretty much limit to FCC, HCP, BCC, and then you do an enumeration, you train, and you assume that your potential would relax only to those. And MTP doesn't. So MTP can discover new, those crystal symmetries that were not put in there. So let me, I have to hide the controls, sorry. So, right, so this picture, I hope you don't see the chat. It shouldn't occupy the space. I'll minimize. So this kind of structures, if you didn't include this strange lattice type in cluster expansion, you have no chance of getting this with cluster expansion. So MTP is strict improvement, and that's pretty much the motivation for starting this work. So we did it with Gus Hart, and after I showed my on-lattice result, he said, this is cool, but I really don't want to do it on lattice because many interesting applications, you can just not assume you live on the lattice. And then we started this work and we did it. Okay. So long name, Chandrakesh Roshan asks again. Okay, so I think he was satisfied with my answer. Ivana Lenik asks, impressive work, Alex, thank you. Can you comment on actual speed of your MLIPS compared to GAP-SNAP and I think it's Baylor's neural network potentials? What about parallel implementation of LIP scaling with number of cores, the largest system you have simulated so far? Yeah, zoom autocorrected, I think I understood it. Let me go back, where is it? So MTPs are faster than any of those. I mean, you can pretty much see everything from where, here, right? Boom, 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 boom. You can pretty much see everything from this graph, right? So MTP is the fastest. Next ones are neural networks. I believe neural networks would be a bit better if you take lots of data. If you can generate 10 times more data than needed for MTP, then it would continue going down, right? So this are about half of the order of magnitude. This is SNAP, it's about 1 order of magnitude between MTP and this, and these are GAP. GAP are most expensive. There are 2 orders of magnitude difference between the best MTP and GAP. And GAP actually can be a little more accurate than MTP typically, the price of 2 orders of magnitude. Right, parallelization, per-atom parallelization works very well. So you can download, I will show today, probably I'll quickly touch on this, but yeah, you can compile parallel lamps with MLEAP. You cannot do a calculation. You can automatically learn on a parallel simulation, but after you train the potential, then you can run many thousand atom simulation in parallel. The largest simulation I did, I think it tens of thousands of atoms with this dislocation, and probably, I think Evgeny Podrybinkin is not around, I didn't invite him. So 10,000 to 100,000 atoms is something we did. So it's still, if you look at this, EAM is typically here, right? EAM potentials are here. There's still 2 orders of magnitude between MTP, or maybe 1.5, almost 2, between MTP and EAM. They're still 100 times faster. Sorry, 100 times slower than EAMs. And scaling with a number, of course, linear. It's linear. It's perfect scaling. There's nothing to lose your efficiency. The Dennis Richkoff, amazing presentation. Maybe I missed it somehow, but was it tested on molecular? Right. So molecular organic systems, it's a problem we're discussing with Artem Oganov this direction. I think the basic problem is that you need to account for van der Waals interactions explicitly, because roughly speaking, van der Waals interaction are 1,000 times smaller than the typical covalent interaction, and the organic crystals. If we talk about organic crystals, then it's the van der Waals interaction that determine their properties. And those are, if our potential has accuracy of 1%, it's considered to be very good, but it's still, then van der Waals interaction is of the order of noise. So this is the basic problem. We tested on molecular, so separate molecules, okay. 2 molecules are okay, and we tested it. I didn't show you the details, but we do reactions of in the gas phase with this, it works. Organic crystals, we are moving in this direction. Gilles Frappert, what an impressive method, Alexander. The CSP community will be happy. Question, did you investigate conformational problem of molecular species, dihedral angle? I will need for coordination polymers, MOF systems. So again, this is all included in the MTP. So whatever, if your interaction depends on the dihedral angle, this is automatically fitted by MTP functional form very well. But if you need, so if your properties depend critically on a van der Waals interaction, I would be worried. So we would need to speak about this and see whether you need to, whether you can use MTP out of the box or some extra development is needed. Jonathan William, with active learning, are you essentially interpolating DFT so you do not have to run DFT on random structures? If so, how do you measure the accuracy of your DFT model without actually running DFT? So yes, I very much like to think that we're interpolating DFT. We still run DFT on the training set, right? We select some structures and we run them on DFT. So we may run a very long simulation, but still do 100 DFT simulations. Typically, those extrapolative structures are kind of very extreme structures. And we know that the error on the training set is an upper bound for your actual error. That's how we know the error. And we can't predict, so active learning kind of is an indicator for the error of DFT without running DFT. So I try to explain it, but to go deep, I would need much more time. Ivana Lenik asks, I think there was some misunderstanding from your side concerning cluster expansion. I think the cluster expansion, Ralph Draughts. I see. Okay, so I think Ralph Draughts likes to call it atomic cluster expansion as an opposed to cluster expansion for the on-lattice models. But fine. Okay, this is a terminological issue. Okay, so I need to go back and reread Ivana Lenik. Can you come in? Cluster expansion. I forgot the actual cluster expansion question. Sorry. No, so it was some other question. How do I go back? Can someone copy paste the cluster expansion question to chat so that I see it, please? And then I'll answer the last one. Okay, so someone wish me luck for molecular systems. So I would say atomic cluster expansion functional form is very close to the functional form of MTP. I think the way I treat many components is kind of better, and I expect the 12 droughts will start doing the same thing in a couple of years, probably, I don't know. It has a different way of doing this. So he includes those in the features, the multi-component interaction, and I include those in the radial functions. So this is the difference. The price I pay is that my potentials are nonlinear, and I have to, it's harder to optimize those, but we overcome those. And one more thing, active learning is another difference between MTPs and atomic cluster expansion. Yeah, okay, I'm not sure whether that was the right, whether I understood the question, but anyway, so this is the comparison. I think that's it. Sergey, what should we do now? Are we done? Yes, I'm a little bit over time. So thanks a lot. I like a lot your questions. Thanks very much for your attention. So those who are interested to do some hands-on experience or see how I do it, I wait you at 4:45. I cannot do it for 1 hour. I'll still run it for 45 minutes, the tutorial. Thank you very much. See you soon.
Okay, thank you very much, Alexander. Very interesting topic. So the next session is tutorial session with Alexander Kvashnin, variable composition structure prediction.
Yes, I'm here. So I think we are ready to start it. So before we are starting, I would like to ask whether you look at your results which we ran yesterday. If yes, what did you get from there? So if somebody is ready to say something, please. Okay, still running. Nice. Cubic diamond. Oh, cubic diamond. That's correct. This is correct answer. All of you who run the VAS calculation at the pressure should obtain cubic diamond. If some of you obtain, so you are successfully finished this tutorial and obtain correct structure. Then I guess we are ready to go to next mode of our evolutionary crystal structure prediction algorithm, which is variable composition mode. So as Artem told yesterday on his lecture, this variable composition mode allows us to find stable structures, binary, ternary structures, and search for stable structure among the all compositions between pure elements A and B. Okay, let me share my screen. Okay. Yes. So, do you have the printed version of my tutorial? Okay, I cannot see chat. I got several strange structures. I couldn't use them properly with Vesta. What kind of strange structures? Can you maybe share the screen and show us just to understand what kind of structures do you have? Okay. So here's the link for tutorial materials. So there should be the name of T03. You need to download them, and yes, here, this one. And then we can do it together. So let's log in on the cluster for those who have account to them. Then my directory. So then we need to write down the command in order to upload data for tutorial. The command is written in the file. So let me look at it. Yes, this one. Yes, so again, you need to load modulus for USPEX. It's module load Python version 3, then USPEX version 10.4, and also need to load Gulp, because this example will be working with Gulp. So Alexander wrote, "This is my problem with Vesta." Probably yes, but what about the data in the best individuals? Do you obtain the space group 227 for the best structures? If yes, that it's likely it's diamond. So okay, then we need example for variable composition search, and this is example number 12. So we need to write x minus c 12. It's called variable composition with Leonard Jones and Gulp. So yes, and then let's look. So you need to obtain these three folders: reference, specific, submission, and input.txt file. Then let's go into the input.txt file. So the difference from the previous examples are the following. In the calculation type line, now we have 301 mode, which means that we will predict three-dimensional, non-molecular with variable composition. Other lines are the same. In the op-type block, we've got number 1, which means that we will optimize energy here. Then atomic type. Here we have two atomic types, molybdenum and boron. So we will try to predict stable phases in this molybdenum-boron system. Then another difference from the fixed composition search is the block num species, because in previous example we just specify here number of atoms in the unit cell, and here we need to specify this kind of block which shows you the borders from which how we should vary our atoms. So first line means that we this is line 1, 0. It means that we will vary molybdenum and not boron. And second line means that we will vary boron. So we independently will vary molybdenum and boron atoms in our structure. Yes, we also so what's next? For variable composition search, as we have also composition which can be changed, we need to specify a bigger number of structures in the first population and in the subsequent populations, because we have larger configurational space. Thus, we need to sample much more structures compared to fixed composition search. Because in previous examples, we have 30 structures in each generation, but here we need sufficiently larger number. In these examples, we have initial population size 200, and each succeed population size is 120. What's next? Number of generation is also should be larger, because our search will take much more time compared to fixed composition search. All other, yes. Then we can notice 3 new lines compared to fixed composition search. The first line is first gen max. It's called first gen max, which means a number of different compositions which will be generated at the first for the first population structure, which will be generated randomly. So as we have system AB, we can randomly generate AB, A2B, AB3, and so on and so forth. So this number limits the number of potential compositions which we should to generate. If you will specify here small numbers, so we will have in this case small variety of different compositions, and our search will go in a wrong way, and we can find only some local minimums because our composition space would be too small to perform good calculations. So by default, this value 11, but again, if you will try to perform some variable composition search, you can play with this number and understand how it works for your system. Then 2 lines, min add and max add, which means that we specify here the minimum number of atoms in our unit cell for each structure and maximum number of atoms. And all the structures will be generated within this range from 8 to 18 atoms. Then we have block with variation operators. Here you can see that we add non-zero value for transmutation operators and some other operators, because here we have 2 types of atoms and we need to mutate also the composition during the variable composition search. Okay, then we move to the end of our input file. So here we have ab initio code number 3, which means gulp, as we did yesterday. Here's 4 steps of relaxation, but in my tutorial I reduce the number of relaxation steps to 1, just to save some time and make this example faster. I also test this example with 1 relaxation step, and it works fine and predicts nice structures. Then we use command executable gulp. So does anybody have questions for this part? Default values first gen max is 11, and this value is yes, for sure it is in 10.4 version for sure, because it was in all previous versions. So this value is in each version exists. Do we need numcalc and which cluster? That's correct questions. Yes, I think we need to specify here. In the case if you'd like to run USPEX directly here on your laptop, for example, on the head node of the cluster, you don't need it. But we don't need to run it here on the compute node, so we need to copy the which cluster and non-parallel calcs from the previous example. I think it would be the best way. So we have example from the gulp example, I think. No, I have. Okay, so number of parallel calculations should be 1, and which cluster you can specify 0, and in previous examples, just to run gulp using the same job in queue as USPEX. So question from Lucas. Sorry for repeating. I made similar question yesterday. Should we always make a variable composition calculation when we have no idea what the number of chemical formulas can be limit the composition of something? Okay, I understand your question. Yes. Okay, let me explain. So first part of the question, make variable composition calculation when we, yes, usually if we start to solve some problem related to crystal structure prediction, we almost have no idea about the correct number of formula units in the unit cell, right? In this case, we need to think, we don't need to choose very small value, like, because if you have two component system, it's very strange to use, for example, minimum number of atoms as 2, right? And basically, we need to choose some reasonable number. And usually for most of the single crystal materials, the range from 8 to something 20 is reasonable. And usually most of the structures can be predicted using this range. There are also special cases when you cannot perform good structure using such small number of atoms. You need to consider, for example, 40 or 50 atoms unit cell, but this depends. As I said, usually from 8 to 20 atoms, that's a good choice. Can we limit the composition? Yes, for example, here in the block. So if you will limit the composition, it means that you will perform fixed composition search, right? By the way, maybe you can turn on your microphone just to have a conversation about it, just to make questions clear for me.
Can you hear me?
Yeah.
The question is like, maybe I have a composition I know, like A2B, like 2 A's for 1 B, but I don't know what the number of chemical formula is. So it might be 2 formulas, 3 formulas. I don't want things like AB2, AB4, but
okay. Yeah, I see the question. So it would be the fixed composition search. So in this case, you need to specify 300. Here, for example, you need to specify 21, right? If you have, for example, 8, right? And then you need to add these two lines, min add and max add.
Okay.
Yeah, in this case, you also will have the range of atoms in the unit cell, the range of chemical formula units in your unit cell.
And this is the section you tell me about, like from 8 to 20 or something more, like it's in these variables.
It's total number of atoms in the unit cell.
Okay, thank you.
Yeah, so if you have composition 2, 1, so the minimum number of atoms would be, for example, 3 or 6, and so on.
Okay, now I understand. Thank you.
Okay, great. So let's back. Okay, does everyone prepare your input file? And you also need to need to copy your run USPEX file from previous example or from TMP tutorial 1, and there is run uspec.gulp.sh. What if we do with 301 and composition and the composition block? I know that previously we can do this, but I think I need to ask my colleagues who maybe knows better about, can we do such kind of variable composition search with a specific number of compositions?
Yes, you can, Sasha. You can. What you can do is to use the so-called anti-compositions. I think we called it. You can look in the manual. You need to provide a special file where you exclude specific compositions, and only the remaining compositions are allowed. This way you can do it.
But I guess the question was about, can we use 301 mode to predict only these compositions? No?
No. 301 is, well, you can exclude all compositions except one. This way you can, but what's the point? If you want a specific composition but with variable number of formula units, then what Alexander showed is correct. You use 300 and specify minat and maxat.
Yes, and anti-seeds is exactly if you would like to exclude composition from the consideration of USPEX.
Anti-compositions, not anti-seeds. Anti-seeds is slightly different. It's structures which you want to penalize. And anti-compositions are compositions which you strictly exclude from variable composition search. Just a little remark.
Yeah, okay, thank you. Yeah. So yes, then let's copy the run file for Gulp. Look at it. So here we will run on one core, we will run our Gulp, and we will run USPEX, and USPEX will run Gulp. And we don't need these two lines again. It will not resubmit it. So if you did all these steps, you can submit it to cluster as batch run gulp sh, and then look at the log file. So please write something if you submit the job, just to understand that everything goes well. Okay, works fine. Yes, and basically, if you will look at the log file, you will find such kind of lines that you can see here, that structure 1 is generated with the composition 15 to 0. It means that pure molybdenum in our case. Second structure is pure boron. Then we have different composition 11.1, 3.15, 6.10, and so on and so forth. Many different structures with different space groups and different compositions. So we have here 114 structures generated with random space group generator, and all other structures are generated with random topology. Is the last structure the best, most stable one? This is question related to fixed composition search, right? Yes, the last structure in the best gathered postcards is the stable one, and the energy for the structure you can find in the best individual. Also, the final line corresponds to the best structure. Yeah, so we have 200 structures generated. I guess it is quite long procedure as we have lots of structures, and then again you will find lines that structure one is relaxed, everything goes well. You will relax 200 structures. After that, the variation operators will start to working. They will generate new structures by using heredity, using random topology, random symmetry, transmutations operators, soft mutations, and other operators. Oh, we have another question. Can you send me the run USPEX file to? So the run USPEX file is located. So are you running on our cluster, right? So for those who are running jobs on our cluster, the sh script for this example is located here. I send the path. I am trying to do the calculation with VAS, but the optimization step don't even start after the structure generation. So run up, right? Can you turn on your microphone?
Yes, sir.
Yeah, so what do you mean by saying optimization step don't even start? Have you looked at the calc fold?
So I'm doing the calculation with fast. I'm not using gulp. But once the structures get generated, the structure has to be optimized, right? But then the optimization steps don't start. Am I doing something wrong here?
So
in submission file or somewhere?
Yeah, so all structures were generated, but
yeah,
nothing happened. So you need to go into the calc fold 1, I guess, and look there whether the input files for VASP creates or not.
It says that after the structures get generated, it says fail to connect to X server, and then nothing happens. Optimization doesn't happen.
So that's something strange which is not related to USPEX, I guess. So have you run it on our cluster?
No, I'm doing in my own cluster.
Yeah, so I guess there are some internal problem maybe with the with your VASP, or I don't know actually.
Maybe in submission folder or something.
Yes, true. If your system on your cluster differs from ours, you need to change the submit job file in the submission folder according to your system of your cluster.
Yeah, probably I have made some mistake there. Can you please tell me how and what should I change in the submission folder, please?
So you need to go, if you see my screen, need to go to submission folder, then submit job local.
Okay.
I guess yesterday the head explained this stuff, and change these lines according to the system of your cluster. change this and change this. After that, I think everything would be fine.
One more thing, I have downloaded USPEX 10.4, but then after installing it's written 10.3. 10.3 is installed, but I have downloaded 10.4.
I guess they had explained it yesterday that they didn't check the number of the version, I think. Yeah, if somebody can comment this, the head or Artyom or Vova.
Thank you.
I heard that as well, that they didn't change the number.
Yes, I think they had told about this. So if you downloaded 10.4, it means that you downloaded exactly 10.4, but the number digit in the name is 3. So don't worry about it. It's a good version.
Thank you.
Does everybody run your calculation? So, question. Can I get some content equal to the file called composition? This is perfect. Yes, that's correct. You need to specify anti-composition file. Yeah, it should work in the same way as compositions. Yeah. How long this calculation should be? Actually, we can look at my example. So I ran this calculation on November 10th, about 12 a.m. and then yeah, it was like 1 day, but we don't really need to wait for 1 day. I will show you the results now, but you can you don't need to cancel your job. Just wait. Maybe tomorrow we will look at the example of the result. So, as in the previous case, in the previous examples of fixed composition search, we obtained the files with called best gathered postcards, best individuals. But here we have information about composition because yesterday it was only one number because we have fixed number of items. Here we have various compositions, and we also can understand using which variation operators or how this best structure was obtained. And also in this case, we have not only one structure which is the best from the one generation, we have a several number of structures which corresponds to different compositions which can be stable. So, and from generation to generation, the number of best structures changes. And you can find here that the origin of some structures is named convex hull, which means that this structure is located on the convex hull, and we can then look at the information about convex hull also. And we have new file called convex hull. And if you look at the information in this file, you can see that this here the only structures, composition of the structures that are located on the convex hull is written here. So in the first generation, we have structure of pure molybdenum, pure boron, and two structures with composition 610 and 5,6, which are located on the convex hull. And then from generation to generation, you can see that compositions of structures that are located on the convex hull changes. And then at the end, we have 5 different phases that are located on the convex hull. But this number is not so informative. We have also the picture called extended convex hull PDF file. Yes, and it looks like this. So here you have enthalpy of formation. Here you have the composition from pure molybdenum to pure boron. And in our case, after the USPEX finished, we obtained 1, 2, 3, 4, 5 structures which are located on convex hull, and they are thermodynamically stable with different compositions, as you can see here. And the whole information about all these phases you can find in extended convex hull file. Previously, we looked at the convex hull, but now please look at the extended convex hull file. And here we have all the information which we require. So we have, again, idea of the structure, composition, calculated enthalpy per atom, volume, and fitness. In this case, the fitness is the height above the convex hull. So this is this value from the convex hull to the point. If the point locates on the convex hull, the fitness is 0. For example, for this point, for this structure, fitness is not 0. We need to calculate the distance from the convex hull to this point. Are black dots in the plot represent last generation of convex hull? These dots represent the convex hull obtained for all structures calculated up to this generation. So it's not only for the last generation, it's convex hull updated each generation. From generation to generation, this convex hull updates. Yes. So for example, if you will go to folder, to each generation folder, for example, third generation, you will find the extended convex hull. You can look here and you will find the red points that are added here within the generations. Then you can go, for example, to second generation and open extended convex hull. And there you will find green lines are structures from previous generation and red points are structures from this generation. They are added here and convex hull is updated. And from generation to generation, then we obtain new structures that added on the convex hull, and from one step to another step, the convex hull usually updates. This calculation was about 1 day. Yes. So the third generation was calculated at 12 AM at the midnight, and the calculation finished at 9 PM. Yeah, so this 21 hour. So let's go next. Also, we have extended. We are talking about the fitness. Yes, in our case, fitness is a distance from the convex hull to the point. Those structures that are stable, they have fitness 0. So here you can find that these 6 structures, they have fitness equals to 0, which means that they are thermodynamically stable. Then we have structures with non-zero fitness, which means that they are located above the convex hull, and there are many different structures. And all these structures coordinates, and you can find in the extended convex hull postcards file with the same order as the extended convex hull. Question: if we run 3 elements, will we get the triangle looking picture? Yes, you will get this. If you'd like, I can show, or maybe not, maybe yes. So I have some ternary systems, for example, if I will find something. Yes, in the case of ternary ABC system, if you will perform variable composition search, you will obtain such name of your elements and diagram and formation, and they will look like triangular phase diagram. It will look like this. Maybe like this. Yeah. And everything is similar to binary system, except that we will have the coordinates, triangular coordinates for each point. So this is pretty much it about the output data. Yeah, so the important point is that here, if you will go to specific folder, you can find that for interaction between molybdenum and boron atoms, we use Lennard-Jones potential. So it is a model potential. It doesn't describe the real interaction between molybdenum and boron. And even in this case, if we use some model potential, we can obtain some reasonable structures. For example, we can let's visualize those structures which USPEX predict to be stable. It is extended Convex-Hall-Poskars file. We can open it with Vesta. Yes, and the first structure is pure molybdenum. Okay, looks like it's correct structure. Then we can go next. Next is boron. Of course, this boron structure is not the alpha or beta boron. This is some hypothetical boron structure. But still, as I said, we use model potential, so we don't need to obtain some realistic structures. For example, then we have molybdenum boron phase. In this case, you can see that we have graphitic-like layers of boron between the molybdenum atoms. So this is structural motif of boron is present in many borides of transition metals. So even in this case, we can predict some realistic structural motifs of our structures, and the composition also molybdenum boron, which is also stable in real life, but with another structure. Then we have composition molybdenum boron 2. So if we create the supercell, maybe it will be yes. And this molybdenum boron 2, it doesn't have the structural motif of real MoB2, but it has structural motif of aluminum B2, where we have graphene-like layers of boron alternating with the layers of molybdenum. So this is definitely realistic structure, which can be observed in many materials, as I said, in aluminum boron 2, for example, and we can predict this material within even using the Lennard-Jones potential with very fast parameters for optimization. What is next structure? Next is molybdenum boron 8. So this looks strange, but still, let's try to construct the supercell. It looks interesting. Yeah, it looks very beautiful, even if it is unrealistic. Okay, my calculation has moved on to generation 2. Oh, congratulations, it goes well. So next we have molybdenum boron 12, even more unrealistic structure, but still fine. And then we can look at some metastable structures and goes on just to looking for something interesting. So here is again some alternation of molybdenum and boron. Yes, now that is it, what we can obtain from this type of calculations. So of course, if you will use not the Lennard-Jones potential, but use a good potential for a system, or even if you can use VASP for this, you will definitely predict good structures which can be observed or even observed in nature. So do you have any questions? So if no, I think we can finish my tutorial because the tutorial by Alexander Shapev should start at 4:30, right? Need to check.
No, it's actually 4:45.
4:45. Yeah, but still, I'm finished with this tutorial, and as nobody has questions, I think we can have a break.
Yeah, let's have a break till 4:45 then.
Yeah. Okay. Thank you for to listen. Oh, okay. Question, please. In our supercomputer, have you loaded the calc? And what was the error message in the log file? So maybe it would be better to use your microphone to explain. Okay. Okay, Alexander wrote, thank you. Oh, thank you. And I understood what was my problem. Now the structural book says, oh, great. Great that you can solve your problem. So now everything seems to work in your case. That is great. Okay, again, this common not found. Have you loaded the USPEX? Because it seems that you didn't load the model with USPEX. Yeah, maybe. Yeah. Yes, when you reload it, everything will go well. How much time general calculation take with quantum special loss? So it depends on your system, of course, and also on the resources that you have. But generally, it's about from 2-3 weeks to maybe 1.5 months, maybe more. For example, yes, I think to finish the variable composition search in binary system, I still it's in average it's about 3 weeks, something, maybe a month. Yes, before restart the USPEX, if you have some error, you need to remove still running or not yet, or even write the command. This one. minus clean, and it will remove all files which you don't need except the results folder. So, for example, here I have still running, I have seeds, I have something else. If I will this, after I've got only those folders which I need. Okay, thank you to participate in this tutorial and to listen me. General question sounds the composition of stable at high pressure, how to find it. Usually to study the stability at high pressure, you can either use several USPEX calculations, several variable composition search at different pressures, or use the vast calculations of enthalpy at different pressures, and then look at the dependence of enthalpy on the pressure for each phase and try to understand where it becomes stable or not. But the best way is use the variable composition search at different pressures and then combine the data and construct the composition pressure phase diagram. So this cannot be done within one run. You should perform many searches at different pressures. So the number of initial code of WASP is 1. So in the block with here, you need to specify 1. It would be WASP. So, and all this information you can find in the manual 1 is WASP, 3 is gulp, 4 is lamps, and there are many others.
Hello. Can I ask one more question?
Yes.
For example, in continuation to my question, variable composition method. For example, I did the calculation at 0 GPA, let's say 30 GPA. So I got a different composition at 30 GPA. 30 GPA. So it might exist at 20 GPA or 15 GPA, may be possible at 10 GPA. So do we need to
Sorry, I don't hear you well.
Can you hear me now?
Yeah, maybe a little bit better.
Can you hear me now?
Yeah.
For example, I did a variable composition calculation, let's say at 0 GPA and 30 GPA. So there is a new composition which is stable at, let's say, 30 GPA, and it's not at 0 GPA. So do I need to do a variable composition calculation at 10 or 15 GPA somewhere, or do I need to look at the enthalpies of the pages and try to locate in between, and then decide the pressure where I need to do variable composition method or fixed composition calculation?
I think first you need to calculate the energy of this new phase at the lower pressure where you didn't find it. Try to find out whether it's on Conway's hull or not. Yeah, and then decide, do you need to perform variable composition search in the intermediate pressure or not. It depends on your step on the pressure, which you already done.
Okay, thank you.
Yes, actually in the chat, Gilles Chapin write you the answer, exactly what I'm trying to say. Yeah, this is like a procedure how to do it. So Bushan one, make sure. Okay, is it question or solution? I guess it's solution. Oh, it's a solution. Okay, thank you. So I think I will stop sharing my screen, and then, okay, let's have a break. If you will have some question, you of course can write on our forum here. You can write here question, and we'll try to answer them as soon as we can.
To speak. I never conducted tutorial with this many people online, so I don't know how it's going to go. Anyway, let me share the screen, and we will start. You should see my screen. Ivan, you see my screen, right? Can you?
Yeah, right. I can see.
Good. Okay, let me minimize the the Zoom controls. How do I do that? Well, it will take me some time. I'm messing with the Zoom controls. So I have huge Zoom controls. Maybe I just press Alt, or what do I do? Who can tell me? How do you don't see my Zoom controls, but they're like taking my entire browser's upper panel.
I thought that if you just like don't touch them, they go away.
If I just touch, if I just click on it, no, yeah, that's what I thought, but it doesn't. I cannot like move it. Alice, are you gonna admit people from the waiting room, or should I do it? Okay, I think Alice is doing it.
There is just one person. There was just one person, but not specific name. Yeah,
Okay.
I'm admitting them.
Okay. Anyway, let's go ahead. Let's not wait on. So, so here's what you do. So we tried to make it simple, but we didn't put so much effort. So if you find a way to do it simpler, you're certainly welcome to suggest how we do it. So mlip.scaltag.ru. mlip is the abbreviation for machine learning interatomic potential, and there are two things that you would need to do. So here, I had a question. Is there kind of a document for the tutorial? So we will go through this. If you go to documentation and then tutorial, there's a link. And this is what we're going to do in the second part of the tutorial. In the first part, it will be like an installation party. Okay, so anytime you go back here and you can do the tutorial by yourself. And then we'll get feedback from today's session and we will update the tutorials at some point, but not now. Okay, so the first thing you do, you go to registration. There's already like a few people did it. Not everybody did it correctly. So you fill the registration form, your full name, email. Now, gitlab.com username, which means that the first thing you do is you go to gitlab.com. And it's not GitHub, okay? So the wrong thing to do is go to GitHub. I believe some did that. No. So if you see this, this is the wrong thing to do. You go to gitlab.com. This is how the design looks. I'm already logged into my account. But otherwise, let me see. Basically, let me sign out. Okay, cool. Yeah, so here you should say register now and fill the registration form. So username is something you will need, right? After you fill the registration form, this username is something that you should put in here in the MLIP registration form. Institution in full, used to say affiliation, not everyone understands. Optionally, your advisor, I know some people, it will be interesting for me to see. And alternative email, maybe sometimes we will duplicate our emails too. Once in a year, we probably will send some emails about important updates. And important thing, you agree to the terms of use. Basically, that says you cannot distribute the code. You cannot, you cannot distribute the code. You cannot use the code for commercial research. And if you publish the work with the code, you are supposed to cite. It's actually written as like you don't need to cite. It's actually, it's an academic norms to cite. So if you agree with the terms, then probably someone has already registered. No. Right, so someone updated, yeah. So then I'm still manually processing those forms. I will add you to a GitLab account. Okay, so let's go a little slowly. I'll wait for a couple of minutes and then I will stop the screen share to protect your data. So you have basically 2 minutes to register in GitLab and there. Then whoever is registered, I will add you to the repository and then you can continue. Okay, 3 minutes. 4:55 p.m. Moscow time, we'll continue. Actually, if you have any questions, you can ask. Let me see if anyone has written to the chat. Not yet. Ah, 11 registrations. Okay, so if you, let's see. Now I will send probably to save time if you register. Again, I'm getting some registrations and I'm copying the username and GitLab does not find those usernames. Okay, so should be. No, second email, wrong username. Wait, hold on. So just in case, I just processed 3 emails and there were no GitLab usernames that were sent. It's GitLab. GitHub is wrong. GitLab is right for this project. GitLab. Okay. What's going on? Maybe it's a bug in GitLab. Oh, it's because I signed out. That's why I cannot add. Now I understand. Sorry, that's my problem.
So Alexander, do we need lamps?
For today's tutorial, not necessarily. If you don't have time to do it, you can cover that part. It will be a small part of this tutorial, the lamps.
Okay, thanks.
Okay, a little bit faster now. Okay, 1, counting how many people I'm adding. 1, 2. Okay, this one I still cannot find. Okay, sorry. So I'll not be able to give feedback on everyone. So I'll just try to add.
Alex, what
Yes.
about the question from Denis Rычkov? I don't know the answer actually. Please read the chat.
Well, I cannot read the chat now. Can you read the question aloud?
When one register, he also needs to confirm it from the email he gets. This may be the reason no GitLab account names. No?
Oh, okay, yeah, you may need to confirm it by email. That is probably true. Your the
Probably.
GitLab account.
Mhm.
Probably yes.
Probably yes.
Okay, I'm half done. Okay, 6 left, 5 left. I mean, I thought, yeah, GitLab.com does not allow spaces in usernames. I think if you send something with a space in the username, it's not a username. Okay. Yeah. Okay. So I'm about to add a number of people. Boom. Takes time. Users were added successfully. So I'll not have later, I'll send an email to everyone, but we'll probably have to continue now. Oh, there's more. No, I think I did it. Sorry. So if I did not add you, I apologize because it just takes time. So those who were added may continue. Otherwise, you would just need to see what I'm doing, and you can watch the recording later. So I will again share the screen. How do I do it? Yes, that's how I'm sharing the screen. Let me read the Ivan, is there anything interesting in the chat?
Yeah, one question. You know, Bushenk wrote me that he already has a GitLab account. Should he send you something about registration or not?
Yeah, so if you don't need to register a second account, just send the details of your existing GitLab account.
I suppose nothing else.
Okay, so after you have done, you will see this repository in gitlab.com. We'll minimize the chat. And there you will see, I already have the SSH key, so I can clone with SSH. Otherwise, you can clone here, or there's a way to download. You can also download the repository. It's still better to clone because you can raise issues here. It's easier to answer. And then I'm going to newly created folder. So the first thing, now we're installing the mlib version. I say git clone, and I copy paste the name of the repository. And if you were added successfully, that will be it. It will take time because it has some heavy files. Otherwise, will be automatic. It's done. So with the other one, you probably would need to enter your username and password here if you do it with HTTP, but otherwise it should be done. Can you send the link, please? Link to what? Oh, this link. Yeah, sure, I can send.
This one. Mm-hmm.
Yeah.
I can send it in the chat, Alex.
Okay, yeah, I just do it. Okay, I'll just wait for a minute for everyone to catch up. Enter your passwords and usernames. Okay. Yeah, that's the command. If Ivan just sent the command, what to do if you don't have the SSH key, if it's just a newly registered account. You don't need to do it on the supercomputer. There's one part I'll show you. The training has to be done on a supercomputer. Again, we designed a tutorial so that you don't need to do training. Otherwise, you can just do it on your personal computer if you are using Linux. On Windows, you don't do this. You cannot install it, this version at least. All right, I'll continue. So I use Midnight Commander. That's what it is. This folder mlib2. And well, there's the same license actually with the MTP potentials. So actually, I should say our paper got accepted that describes all this. So very soon there will be paper that you can follow. Otherwise, for now, it's a recent. Actually, Ivan will say the archive version of the paper. It's a kind of tutorial paper that covers it.
I'm sending the archive version, Alex. I'm sending it now.
So the first thing you need to do is to configure. And you can just say configure, or you can see the options. So the interesting options are no MPI. I don't know why you want to do that, just maybe for testing purposes. Otherwise, it will detect whether you have MPI or not. Compiler, you can force one of the two compilers. For me, it would automatically detect Intel, and that's probably it. Yeah, so we used to have lamps, but now lamps in a different repository. So I'm running configure, and then I'm saying make MLP. And by the way, what I should say is this. There's a README file that you probably should start with. Let me see. So getting started. Yeah, this is a README file. It's very small. And install.md is the detailed install instructions. So you can go through these install instructions, or we put in many different pictures. So you can go to the tutorial. So maybe this is a part of the mlib.com. If you go documentation tutorial, here's the link. Ivan will post the link in the chat. And so I go, and this is, so now we kind of have first tutorial. So installation instructions, we call it tutorial 0. And basically, okay, we repeat these steps. Okay, so now we clone the repository. Dot should not be here, by the way. So now we're doing this. We ran configure, it detected your compiler's MPI environment, and now we should say make MLP. I'm doing many presentations these days. Make MLP, I do compiling on 3 cores because some of the files are pretty heavy. It will take a minute to compile. So the recommended are Intel compilers and MKL library. This way it runs faster, especially if you want to benchmark this against something. Okay, it created the folder called bin, and there's an MLP binary here. We can actually start. It says MLP, it's MPI version, 1 core, list of developers. Ivan is one of those. And you can actually self-explore what it does by just running it and then running mlib help, which is this message you don't need to do, and then mlib mlp list will be list of commands. This is something you can self-explore. Okay, let's actually continue going the tutorial. Yeah, so there's also instructions how to compile LAMPs with MLP built in. I'm not going to go through them today. Okay, so we're gonna go back and we're gonna do the tutorial number 1. Okay. So again, if tutorial number 1 follows the example 1 of the archive paper that Ivan sent. They're a little bit different because we converted it to the tutorial. So basically, the first thing you should say is obtaining the input files. There's no link to the repository. No, it's actually exactly the same repository. So it should be a public repository. You should be able to clone it. It's called tutorials. So if you go, Ivan, later we should put the link.
Yeah. Yes, I'm typing it, Alex.
Yeah.
Clone it.
Oh, so this is the tutorial. You can again say clone, and I'll go back in my environment here, and I say git clone mlib2 tutorials. So it will download all the files, and so here's how it looks. Tutorial 1 is the files that you need to do the tutorial. There's also tutorial 1 answers, and these are input files and output files. You can compare, we kind of call it the answers, the output that we got against what you got. And this is the way for you to be able to check. So we go to tutorial 1, and there are 5 different folders, and they correspond to the remaining 5 steps of the tutorial. So I'm going to wiki, going to tutorial 1, step 1. So compile MLP library and install mlib into LAMPs. This is optional. Copy mlib and LAMPs mlib binaries into tutorial 1 folder. So again, I'll not read like a dummy all those things, but we designed a tutorial so that you can do it with your own pace by yourself. Okay, so if I will accelerate a little bit because I have 20 minutes left for the tutorial, but you can just do it slowly. We tried to put instructions very, very clearly. So it says you need to put those files here. And let me do it. So I'll just put the MLP binary. I'll not do LAMPs. Okay. Basically, that's it. README file also contains duplicate of the information that is here. So first, checking the minimal distance between atoms in the training set. So if you go here, so there's test set and there's train set. And these are postcards and in-cars for VASP. Well, we do not distribute postcards just in case, but it's this. If you have VASP, you can create your own postcard and recompute and redo it. But we actually compiled, calculated, and converted to a CFG format. So this is the internal mlib format of those files. And this is the test set, and this is the training set. Right, and the first thing that you're advised to do is to calculate the minimal distance, and it's done with this command: MLP min_dist training set. If I do it, it tells me, oh, the minimal distance is 1.95. Okay, and you can do the same. You can execute this command on by yourself here, and you can execute this command on the test set. It's a little more the test set because there's smaller number of configurations. So it's always a good thing to do before feeding the potential. Let me see the chat. Yeah, Vladimir Baturin actually, right? How to compile on Oleg. So as I understand, Oleg is something that we do. So Alexander asked that she, I believe, cannot git clone lib. So I just added those. So if I did not add you, I'm sorry, there's probably some error. So later, maybe today, I will email everybody and you should re-register the account and send and register, and you will be aided and you can do it. So I'm sorry that we cannot actually fix it right now. So you will need to probably see it in a recorded way. So let's go back. All right, fitting and validation of MTP. So you do fitting, or you call it training with this command. So there's ini.mtp file. It's an initial potential, untrained potential. And this is explained how you do it. So I will quickly show you how we do it. So you either go in the repository and go to untrained MTPs, or there's also untrained MTPs files here for your convenience. So, so the ini.mtp file, I just take this potential. It's level 16 potential, but for that you need some MTP theory. And I copy it over here. And what you also need to do, you can edit some of the fields here. So readme.txt tells you what you can read. There's some so species count, minimal distance, maximal distance, this is cutoff, and radial basis size. Sometimes you want to do it. Sometimes 8 is the default, it's a good value. So here we will change the minimal distance because we know it's a bit less than 2. It's not absolutely required, but we put 1.9 here. And then we can do training. So we created the ini.mtp file. Yes, go ahead, Ivan.
Okay. Did you send confirmation to Alexander? Probably you didn't set her confirmation. She just changed password.
Yeah, so I'm sorry. So this is what I did. There was about 30 registrations. And I went through probably 20, and I could find the usernames in the beginning, and I added 20. And there was about another 10 that, for some reason, the GitLab usernames were not found. I don't know whose fault is this, but I wasn't able to add. And I don't even remember Alexander was among those. Let's do this. Let me quickly try to fix it. I should try to find it in the repository. Okay, so I found Alexandra. I will quickly add her, and we will continue. Okay. So I'm stopping screen share. We're doing this international meeting, and I don't know all the rules about data privacy in different jurisdictions. So just in case, I'm not showing you any private data of the participants. Okay, Alexander, I should have added you. Okay, so okay, so this is how we train. You can do it by yourself. Otherwise, pod.mtp is the potential that that we got. Okay, so now I'm gonna copy it. So this potential, you need to do relaxation with this potential. It's actually already copied. Let's copy here, and maybe copy here also. I can't remember. But okay, we'll do it later. So it says, yes, copy this file to 5 also. We go to step 4. 3 steps remain in about 10 minutes, 13 minutes till the end. Let me quickly read the chat. Okay, nothing up to date on the chat. Okay, so basically this tutorial, I can't remember, it's probably said somewhere. So the potential is for BCC molybdenum structures. And we're gonna do different things. So first things we'll do, we will relax, find the equilibrium structure. And okay, I realize we need to go slowly. It's done with the MLP relax command. And the first argument to the MLP relax command is the relax.ini file. So .ini files, they control how MLIP works. If there's active learning, there's more stuff here. When there's no active learning, it just says MTP file name, pod.mtp, and it's here. We kind of trained it, or at least we pretend. Init CFG is a configuration we are gonna relax. It has supercell atomic positions, and there can be more configurations. It can relax more configurations. It's also parallelized. You can relax 100,000 configurations on 1,000 cores. It's not a problem. Okay, so let me just do it. I will just copy paste this command. It says take configurations from init CFG, save them to relaxed.cfg, and there's stress tolerance and force tolerance. And read more in the documentation about those because there's some interesting behavior. For example, if you put stress tolerance to 0, it will not relax the supercell. So this is also an option of this. Okay. Here, let me try to do it. Boom, relaxed. Wow. So it saved it to relax.cfg _0. And this _0 is because this is MPI version and because we were a little lazy. So I could do MPI run. It would parallelize it over, I don't know, many cores. And for each core, the configurations will be written into different files. So later, this command actually just renames it to relaxed CFG. So this is a relaxed configuration. Human readable forces are 0, stresses are 0. You get the energy. It also does some extra information on the configuration. Okay, let's see where we are. That's pretty much it, right? And then there's also answers. So when you go it by yourself, if you're not following the tutorial, you can always check how it should be in the tutorial 1 answers folder. Okay, 2 more steps. 2 more steps. Give me 1 second. Okay, so the step 5 would build an energy volume curve with this. And you can use lamps. There's lamps scripts that do it. After you make a lamps interface, you can totally do it with lamps. But otherwise, you can also do it manually. And this is how you do it. So this is deformed.cfg. So we take the relaxed configuration and then compress it and expand. Okay, and you can do it by yourself in this format. Pretty clear. There's also somewhere documentation where this format is explained. So there's a few tens of those configurations, and you can compute the energy with MLP calc EFS command. So the input parameters are potential and the deformed configuration, and the output is deformed with EFS. And the EFS, our MLIP favorite, abbreviation for energies, forces, and stresses. Okay, so if you run it, this is the input configurations, just supercell and atomic positions, and the output is this. Sorry, no, it's not this. You need to run it. This is the output, right? So forces, actually, they're not huge. Oh yeah, okay, so forces are almost zero, right? Because this is a symmetric configuration. Stresses are not. So these are stresses in electron volts, the way VASP puts it, and I can't remember about the sign. But basically, plus stress is, the sign is compression means positive stress. Okay, so, or am I wrong? No, okay, there's some artifacts, but basically, so I go to the end, the stresses are negative. Yeah, so I'm right. And outside it's, so, and this is VASP. You already computed, and then Ivan wrote a cool Python code. So basically you need to text process this configuration files, and you get the energy volume pairs that you can later plot. Okay, we'll not do the plotting now, but this is what you do. But basically, it essentially trains you how to do the calcufs command. And if you want to play with the potential, fit it, do different things, this is what you do. Okay. Now we have 5 minutes left. Here's what I suggest. So step number 6, we thought it will be a kind of exercise. So I'll not show how to do it, but the idea is this. So step number 6, we go to elastic constants, and we go to finite differences. And these are, I believe, 1, 2, 3, 4 is a configuration, and 1 is it's expanded in one direction, right? So it's normally 3.16. This is equilibrium, and in the first direction we expanded it. And then 2, we compressed it here. 3, we sheared it, kind of positive shear and negative shear, although they're equivalent. Okay, and what you can do, you can compute those configurations, and then you can use stresses and recompute the elastic constants from stresses. So this is something you can do, try to do by yourself.
I will send the link on how to compute elastic constants using finite differences.
Okay. So, and I think, do we still do it or what? Okay, anyway, so I will let Ivan, so last maybe 15-20 minutes, Ivan will steer the whole thing, and maybe you can ask questions or try to do it by yourself. And you can also do it with lamps. And with lamps, I will very quickly show how it's done. Basically, where's the input file for the lamps? In Elastic. This is the lamp script. And I think what is important is, where's pair? Is there none? Okay, so this is included. So in the lamps input script, when you put pair style, if you did something with an EAM or Leonard Jones, you would write pair style, EAM, pair style, M, EAM, pair style, LG for Leonard Jones. Here, you do pair style mlip. And you put mlip ini. It only works with pair coef star and star. And mlip ini is again something simple. Okay. Maybe I can go to
Alex, one question from one guy, Bushen Wang. Please send him the authentication for cloning, please. Confirmation, something like this, as I understood.
Okay, I need to add you to the repository.
Yes,
and
yes.
I'll do it later. Okay, we'll do it offline by email. You need to register first. I think I've covered it. So so basically, maybe just a few minutes left for me. I will just show you. So this is the repository, and there are examples which are not installed. Let me see if the repository. So I go to my private repository, and so here in the documentation, I downloaded examples. So example one, it's example from the paper. It's almost the same thing. You can do it by yourself. Example two is molecular dynamics with active learning. And it's a bit crazy. Let's go to the input files. So basically, the mlib.ini file for active learning looks like this. So MTP file name pod.mtp, and then you say select, it's active selection, you say true, and then you put thresholds. And again, if you read papers, you will understand, but these are good parameters for those. And you save selected configurations to a file. So this is how you do active learning. And it means that if the threshold exceeds 3, they're saved to this file. If the threshold exceeds 10, the simulation is broken. And this is something you need to create this active learning state. So again, the paper describes it pretty well, I would say. Many people already could do it by themselves. So this is something you can do active learning with, okay? That's probably it. I don't have time to do anything else. The chat is empty. So I will thank you for participation. Again, I apologize that I could not add you very fast. So I will just, some point later in the evening today, or maybe tomorrow, I will add you to the repository, and you can go through this at your own pace by reading the tutorial or going to the recording. It should be on YouTube. Okay, thank you very much. I will leave you to Ivan. I think you have good 15 minutes to do things. I would suggest you ask questions mainly.
Probably yes, ask questions to me.
Okay, thanks.
Yeah.
And bye. I'm sharing.
Also, in the case of questions, I'm writing my contact email here in the chat. What do you mean by speed between mlib and lamps?
Yeah, we tried with the gap one, and then like it turns out to be pretty slow. Like if we run the lamps using the machine learning potential constructor using gap, so it is not comparable. It's about 1 order of magnitude slower than the classical
Yes, I understood this question. Yes, unfortunately, machine learning potentials are of magnitude of order of magnitude slower than classical potentials, yes, but they are order of magnitude faster than DFT, so this is feature. So yes, that's true.
But is there a solution like running such things on GPU or like kind of in parallel?
Say it again, which solution?
So to run the molecular dynamics using machine learning intermittent potential on GPUs or like in...
on GPUs, no, not yet.
Okay.
Only with MPI.
Yeah.
Okay, about WASP output, Bush and Wang, we have a command, special command, convert CFG. I will write it down here, convert CFG. it is able to convert configuration from VASP output format to internal MLIP format. In order to write information about the commands, please type this command MLIP list. It will show you the list of MLIP commands themselves. And next, type MLP, convert PFG, help, not this, MLP, help, convert, minus CFG, yes. In this case, you see information on how to convert the configurations. Active learning is a kind of supervised learning, yes. When we automatically, collect a data set, we have passive learning when we collect data set offline, and active learning when we collect data set automatically. That's all. Okay, I'm reading. I suppose, yes. Julio, I can send you the papers. Please write me this question again on my email. I'm sending you a mail. I will send you the papers on this topic. We have already played with convex hull, with stable structures or stable structure predictions, and with molecules. I was playing with molecules with chemical reactions, namely RPMT plus LIP. Okay, my interface solution. Okay, Zhank, I will send this question to my colleague Bahir Maidasavi because he is the main person who is responsible for the connection of MLIP and Shank BT. Okay, I will send it to Bahir. It doesn't support GPU, and we have a special plugin for supporting MLIP pair style for lamps. Yes, we have it. Please read here. I will send you the link. I will send the link in the chat here. follow the steps explained here. This is an open source repository. You can clone it, and then by following the steps, you will install mlib plus lamps version. Then using this style, our mlib style, I will also send it to the chat. Wait a minute. Wait a minute. Give me a minute. Not here. So we add these two strings, I mean pair style string and pair ref string to lamp script, and after that we are running calculation on lamps using moment tensor potential strained. You can also read here, by the way. I will also send it. Apart from lamps with many packages, but it's closed source and we don't distribute it. For example, with IPMD rate for ring polymer molecular dynamics. For example, with ShankBT again, but I suppose you should write to Bahar Mortazavi if you're interested in combination of mlib and ShankBT. Okay, I have 5 minutes left. Okay, how to generate the training configurations? First, we calculate configurations with WASP, and we need output files, the so-called outcome files. Then we use the command like this. For example, I can write it down. Convert CFG. Imagine we have one outcar, for example, one, but we can process not one outcar, many outcars. Then we want to construct training set and write it to train.cfg file. I will send everything in the chat. And we use the following option. Wait a second, I will send it. Like this, we use convert CFG command. Outcar file is input file. Train CFG is mlib internal file, and minus input format is an option that indicates that our file in input format is WASP output, not outcar, WASP output. For details, please read the documentation. MLP help convert CFG.
But my question is mainly, how could you combine this with active learning? Because with active learning, you want to generate some configurations on the fly.
Yes. So, okay, imagine we have potential trained only on one configuration. We have one configuration calculated. Yes. Okay. Not?
Yes.
Yes. Okay. Next. We have the so-called active learning strategy. Imagine we are running molecular dynamics. We have one configuration and our potential trained on one configuration. Next, on the next step, we see the next configuration with other atomic positions. Our program will tell you that this configuration has a very high extrapolation. Again, read our paper for details. And using the so-called mlib ini script, our script with settings, we can do the so-called, we can switch on this active learning mode. And this active learning mode will select configuration to training set. Then we send them to WASP VESP calculate energy forces stresses, we retrain potential and restart molecular dynamics again, and so on. So you should write additional scripts that calculate energy forces and stresses with VESP. You should use, for example, LAMPS driver, and the rest thing, all the rest stuff, MLIP is doing. Active learning, which is incorporated in MLIP, is doing. Is it clear or not?
Yeah, so basically we need lamps to generate the configurations, and then the MLP will judge whether do we need to do calculations on such configurations.
Yes, exactly. Not only lamps, any driver, relaxation, for example. Relaxation is internal driver. Imagine we are starting from, again, the very first configuration, then we are trying to relax. Our MLIP code will decide whether this configuration has a big extension of extrapolation or not. Okay. Then we send it to VASP and any driver. But again, it's very short answer. Please read the paper I sent.
Yeah, it would be nice if there's a tutorial for this. I think this would
tutorial. Yeah, tutorial. By the way, we will write the second and the third part of this tutorial later.
Thanks.
Okay, I have 1 minute and I have to go the very last questions from anyone, if you have. Okay, thank you for participating, guys. Really, it was nice to carry out this tutorial for you. Hope you will use some MLIP code and make a very good research. Bye to all. See you.
Ivan, thank you very much. So we have our next talk by Chang Zhu from University of Nevada, Las Vegas. Chang, are you here?
Can you hear me?
Yes, okay. I can.
Yeah.
So good morning, and
yeah. Yeah. Can I share my screen?
Yeah, sure.
Yeah, I think so. Yeah. Cool. Can you see my screen? Can you see my presentation?
Yeah, we can.
Okay, good. Okay, good evening, everyone. So this is Chang Zhu from University of Nevada, Las Vegas. So okay, by the way, so I'm in the US now. So in the US Pacific time, it's 6:45 a.m. So it's the very beginning of the day, but I know like this is the last presentation of the workshop for today. So I know probably some you have gone through a lot of like talks, also a lot of like tutorials. So you must be tired. So thank you very much for those of you who are still staying in the conference room and who are attending these lectures. So for today, my topic, I will talk about something maybe easier compared to other lectures. So I will talk about how to increase those structure prediction, how to improve the performance of prediction by handling the structure initialization. Okay, so probably you already seen this picture. So in the first day of talk by Professor Oganov. So the topic of this workshop is about crystal structure prediction. So in order to predict the structure for the given materials, so usually we know like, so we have to care about the two things. One is to effectively navigate the structure in the gigantic space. So we have different algorithms. USPEX is one of them. And also, actually, we just had a very nice, we also needed to find a calculate to predict the energy or property for the predicted material structure. So we just had a very nice tutorial by Alex about the machine learning potential to the prediction of the materials energetics based on machine learning potential. It was very nice. I really enjoyed that. Okay, so in this talk, so we will focus on the USPEX. So, you know, like, so now USPEX has been increasingly powerful. So it can handle inorganic crystals and organic crystals. Actually, when before I joined my new position in University of Nevada, Las Vegas, I have been working on the development of USPEX code for for more than 5 years during my PhD and the postdoc. Well, I did my PhD with Professor Oganov in Stony Brook University. Okay, so let's talk a bit about the strategy for crystal structure prediction. So you all know now, this is a global optimization topic. So in order to effectively compute find the ground state for the materials, you needed to develop different global optimization algorithms to scan to effectively sample the structure space. So there are many global optimization methods like random search, simulated annealing, and minimal hopping and Bayesian hopping. But in this talk, so I think most of you will be interested in the bio-inspired algorithms like evolutionary algorithm or other similar types of algorithms inspired by the nature. So we all know like how nature evolves. So in nature, so any kind of animals will develop some intelligence to find some minimum solution with teamwork. So all of these are based on some so-called population-based method. So all these methods will require some strategy in the context of material structure prediction. It requires some strategy to play with the structure space. So that is how to initialize the structure. Here, you have some mechanism to generate the new structure, and then you mutate the structures or generate the new structures based on some selection rules, and then you basically repeat this cycle for many times. So by mimicking the nature of evolution, and then in the end, you find the solution can be proved over and over with the generation by generation until you find the ground state. So, but in the context of the material structure prediction, there are some fundamental problems. So how to initialize the first solution. Also during the structure evaluation step, how to mutate the structures in a smart way. So basically what do we do usually? So for the initialization, we have the following strategy. So you can start with purely random structure. So this is easy to implement, but usually doesn't lead to very good performance. So in reality, most of case, we will use some better strategy. So for instance, random symmetrization, basically which is to generate the structure with random symmetry, or another exciting development called random topology by Professor Oganov's group. So in this talk, I will focus on the second approach, random symmetrization. So based on a new open source code PyCrystal. So before I come to the, before I talk about the details, so let me give you like some brief idea why do we like to generate the structures based on some random symmetry. So there are two reasons. So the first reason is according to the database analysis, people have already found that. So if you grab all the materials structures from the real materials, you look at the histogram, the distribution of the structures by space group, you actually will find that the distribution is pretty uneven. So for instance, for inorganic structures, so actually you'll see the space group, some space groups actually appears much more frequent than the other space groups. This is the trend is even more obvious for the organic crystals. So for the organic crystals, the first 10 space group actually accounts for over 90% of the structures in the database. So that actually indicates that when the atoms form the crystal, they really like to arrange themselves in some like symmetrical ways. So this is one of the reasoning. The other reasoning for generating the crystal, the symmetric structures is because when we generate the structures with symmetry, it usually actually enhances the diversity of the structures. It actually brings up much richer like atomic environment. So which actually will be beneficial for the following subsequent structure search. Okay, so in order to generate a structure with desired symmetry, so we probably need to go back to like some very fundamental stage. So how to describe the symmetry of the crystals. So now I will give you a short tutorial of crystallography 101. So for instance, if we start, I think all of you are familiar with the diamond structure. So here is the diamond structure. So how do we describe this? Use the language of symmetry by using the language of crystallography. So first of all, we can divide them into two parts. So they have, of course, they have the unit cell. So for diamond structure, so it has a cubic symmetry. So the space group, and then it has a face-centered cubic. It has a face-centered Lewis unit cell, and then inside this unit cell, you will see eight carbon atoms are arranged inside this box in some way. So here I just give you like the list of the atomic positions. So when you look at this position, also when you look at the graph, you can see actually these positions are actually, they are not independent. So they are related by some symmetry operations. For instance, if you just look through this line, you will see it's some like Miller symmetry, right? So these two are just basically, they have some Miller relations. So if you actually go through this direction, you will see some like 3-fold symmetry or 6-fold symmetry. So all of this actually can be for the space in the given space group. All of this can be described by a so-called Wyckoff site. So in this given space group, so the atoms mathematicians or crystallographers already figured out. So in order to satisfy this symmetry, the symmetry of space group FD3M, you have the atoms must be constrained by some symmetry operation. So they can only form a few sets of like combinations of atomic based on the atomic coordinates. So for this one, so for the structure of like diamond, it will actually, this atomic coordinates can be categorized into 8A space group, 8A Wyckoff sites. So of course there are many others wife sites. So I will talk about the definition later on. So you see that, so now so far we know, like, so we can describe the structure by symmetry by using the language of crystallography. We need to know the space group. We also need to form the unit cell. And then after you give the unit cell, so you just arrange them, these atomic coordinates into one of the wife sites. If you have many atomic positions, it can be combination of different wife sites. Okay. Okay, now since we know how to describe the diamond structure, so we can actually consider a inverse problems. So how do we generate a diamond, randomly generate a diamond-like crystal? So in this case, so we will do the following. So we need, of course, so the target is to generate a structure with 8 carbon atoms, and also make sure the structure will satisfy the FD3M space group symmetry. So first of all, we can randomly generate, a cubic lattice, FCC, face-centered cubic lattice. So, and then we choose the wife sites from the table. So you already see the table. Because we are trying to arrange 8 carbon atoms. So in this case, you only have 2 choices. Either you arrange your atoms, 8 atoms into 8A wife sites or 8B wife sites, right? So then you just fill the atomic positions based on the table. Of course, you can choose, in this case, you can also choose A to B, but in reality, if they are equivalent, so it's just like some translation. So they are equivalent. Okay, so now let's increase the complexity of the problem. So now, suppose we have, for the given space group, we want to fill 16 carbon atoms. What are you going to do? So in this case, you can you will have multiple solutions. So for instance, you can choose the 16D positions or 16C positions. Oh, by the way, so okay, so the wife sites, the naming of the wife sites is composed of 2 parts. It's basically a number followed some following by some letters. So the number here, denotes the multiplicity. So it denotes like how many atoms does it have in this site, and then the letter is just arranged alphabetically from by multiplicity from low to high. So the one with the lowest multiplicity will start with letter A, and then letter B, and so on. Okay, so if you want to generate 16 carbon atoms inside the space group FD3M, so you will have several choices. It's very obvious. So you can arrange them into 16C wife sites or 16D wife sites, or the combination of 8A plus 8B, right? They are all possible since we don't have any prior information. So you should explore all the possibilities. Okay, so if we further increase the number of atoms, like now if we go to 32 carbon atoms, then the number of combination will increase. So here I just give you this. And also I want to note that, so when you have the wife sites with higher multiplicity, then you will have more freedoms to change the atomic coordinates. So for instance, in the previous like 8A wife sites, so you actually don't have any freedom to change the atomic coordinates. They must be some like fractions, like 1As, 3As, or 8As, right? But when you go to the wife sites with 32E, actually you will see, so now you can change, you can actually play with some variables. You can, it is represented by this. So you can actually assign any fractional numbers into X. So yeah, this actually gives you more randomness. Okay, of course, if you go to like a higher, higher multiplicity, you will have more freedom. At the maximum, you will have like 3 freedoms. So you can assign any arbitrary like numbers to X, Y, Z. So that's the maximum. Yeah. Okay, so after we know, so to arrange this atom into different combination of Y sites, where the key to generate a random structure to satisfy the given symmetry. So then you will have like 2 possible strategies. So since you have multiple possibility to combine this Y of sites, so you will have 2 ways. First of all, you can like what I did here. So you can pre-compute all the possible solutions and then randomly select one. And then for each Y of sites, if they have some degree of freedoms, you can randomly generate some points, like XYZ points. Otherwise, you just generate some, generate the coordinates with fixed points. That is one common strategy, but usually, usually we don't do that. So we actually several years ago. So when I was still a student, so my advisor of Organov, so Professor Organov actually had a different idea. So he said, why don't we actually start with the better so-called metric schemes? So I will talk about this later. So I will talk about this soon. So we can do what? Suppose you want to place 8 atoms into some crystals with some symmetry. So you always start with the desired numbers. So we start with we place 8 atoms into the unit cell, and then if we find actually if the 8 atoms actually their existence exists like very close atomic pairs, and then we merge them. You see, so we can merge them. So and then we automatically we can select the structure. We can select the structures which is occupying like the Y of site, special Y of sites. So this way, actually, we can avoid selecting the Y of sites with 2 high symmetries. So this actually increase the randomness of the selection. Yeah, that's actually the way we are doing in our new code PyCrystal. Okay, now let me talk about some concrete examples. How do we generate a crystals, for instance, molecular crystals? So for instance, if we want to generate a crystal with P2121121 symmetry, so we want to have 8 water molecules in this unit cell. Of course, the program should be very flexible. So if you know the cell parameters, you already know the occupation of the Y of sites, you can pass this information to the program. But at this stage, let's suppose we don't know this, so we want to do some like a random search. We do some random generation. So in this case, so we look up the table of Y of sites for space group P2121121. Actually, in this case, we have a very lucky case. You will have a lucky situation. So there is only one Y of sites, 4A. So we only need 4 molecules. So in this case, what are we going to do? So we will use this table. So we randomly assign XYZ points. So these points will be the center of the water molecules. And then we randomly assign some orientation for this water. Then we get the first molecule. And then the rest of the molecule, the remaining 3 molecules can be generated by by following these symmetry relations. So yeah, that's actually, you see, it's very easy to generate this molecular crystals. Okay, but the situation can be a bit more complicated. So suppose now we change the space group number. So we don't do the space group P2121. We do some space group CMC21. So you will see actually now you have different table for Wyckoff sites. So it has you have two choices, A to B and 4A. Of course, since you only have 4 molecules, so you can only choose A to A, right? So then again, so you just you randomly generate some YZ points for the center of the first molecule, and then you repeat then you reconstruct the other molecules by following this relation. But the problem is this actually can be tricky. So because here, let me see. So so you see there is a, so in order to satisfy in order to place these molecules into 4A Wyckoff sites, it comes with another symmetry constraint. So it has so-called side symmetry. This site, or inside this site, it has one additional symmetry. It has M dot dot dot, which basically means you will need to have when you place this molecule into the space group, you must make sure the molecule itself actually will preserve this so-called M dot dot symmetry. So what's M dot dot side symmetry? It means, so in the BOC plane, so the molecule will have a mirror symmetry in the BOC plane, so perpendicular to the first axis. So in this case, you must place this molecule, which actually in a valid orientation. So in this valid orientation, in order to satisfy this space group symmetry. So of course, this can be very, we have 230 space groups. So each space group has multiple Wyckoff sites. So this actually can be very, very boring if you do it by hand. So luckily, so now in our code, actually, we can automatically detect all the valid orientations and place them into, place the molecule, place this molecule according to the symmetry constraints. So let me give you another example. So for instance, here, so if you want to generate a crystal with carbon 16s, so you want to have a space group symmetry, like hexagonal space group symmetry. So then you can actually, you need to place that, you want to make sure, so the orientation, so the molecule has to be orientated in this way. So that's when you look at this crystal through the Z-axis, it has to pass this kind of center of the hexagons. So that's of course, for a carbon 16, you have many hexagons. So you can arrange them in each positions. So in this case, we can generate a crystal of molecular crystals by allowing the molecules occupying this special Wyckoff site position. By special Wyckoff site position, which I mean the atom. So the positions, they will have some like additional side symmetry constraints. Okay, so here we develop a code actually to consider all the possible cases. So you can generate any symmetry objects like atomic crystals or molecular crystals with the symmetry in 0-dimensional space, 1-dimensional space, 2-dimensional space, and 3-dimensional space. I know probably most of you are working on the 3-dimensional crystals, but if you are interested in the low-dimensional crystals, we can also do some. You can also use this code to do that. So let me quickly go to some. We have some like okay, we have there is just examples. So to explain how to use this to generate some crystal. So you can also see how it look like. So for instance, you can also use this to generate some 2-dimensional. This is actually the case of 2-dimensional crystals. So which means it has periodicity in the XY in the AB plane, but it doesn't have periodicity in the Z axis. Okay, you can also do what you can also generate some like nanoclusters. This is 0D case. So for instance, with this code, you can easily generate something very close to the carbon-60 based on the hexahedral symmetry. Okay. Yeah, so I think, so we have some documentation there. So if I have time, I can finish the talk earlier. So actually I can give you some like demonstration on my Jupyter notebook. Okay, so after you generated the crystal, so another important topic is to change the crystals. Remember, so in the evolutionary algorithms, so at the end of each generation, we generate new crystals based on some variation operators. So if you want to do the mutation operators, you probably will also probably also want to use this to change the crystals. So usually you can have many ways to change the crystal, like you can purely random perturb these atomic positions, but this turns out to be not very effective. And another possibility is to mutate the crystals based on some soft modes. So remember, so in USPEC, we have a so-called soft mutation operators, so which actually pre-calculate the possible soft modes based on some empirical model to do that. So in this case, let me give you another solution. So in reality, we can actually change the, we can also change this, perturb these molecules to make sure so they still observe some like symmetry relations. So the first case is to change the crystals by preserving the symmetries. So for instance, now if we have a water crystal here, right? So since we have the symmetry relations, so you can it tells us, so in order to preserve the, suppose we have the crystal and we optimize the geometry. Now this is the geometry after optimization. How to change this crystal? So you can because we have symmetry information, so for this particular case, you can only allow in order to satisfy the symmetry, you can only rotate this molecule along this given axis. So if you don't have symmetry information, so you cannot do that. But if you do have the symmetry relations, so you have symmetry information, actually this is possible, and also this will be beneficial to generate some like some new crystals with better quality. Okay, another interesting topic is, so instead of just preserving the space group symmetry, you can also change the crystals by letting the new structure possess symmetry lower than the original symmetry. So this is called the space group relation. So what we are going to do here is to suppose we have a crystal, we generate a crystal. Actually, you can see how easy it is to generate a crystal. You just need 2 lines to import the PyCrystal library and then tell them, okay, we want to generate a crystal with space group 227 with 2 carbon atoms in the primitive unit cell. So it will give you a crystal like this. Again, this is diamond. So now what we are going to do, so in order to generate a new structure with symmetry lower than FD3M, so you just need to tell them, okay, I want to generate a new structure, which is a subgroup of the original space group. So also you can optionally tell them, okay, we want to generate some crystals with a symmetry of 141. So in this case, you will see the resulting structure will look very similar to the original crystals, diamond crystal. But here we just need to break the symmetry, we only need to slightly perturb the atomic positions. So probably you don't find the similarity between these two plots, but actually if you just rotate this AB plane by 45 degrees, you can see the trajectory, how we generate this. So what do we do? So we start with this one, and then we rotate this AB plane by 45 degrees. Yeah, you see. So then we get this pattern. And then of course, we will slightly change the atomic coordinates, because in the new space group, so we don't need to satisfy so many space symmetry operations. So in this case, we can actually slightly change this. We can slightly change the positions. Yeah, so all of this can be done by 2 steps. First of all, you need to know the transformation matrix. Secondly, you need to know after the transformation, so what kind of freedom do you have to actually perturb the atomic coordinates? So this is the so-called Weigel splitting schemes. So the transformation matrix and the splitting scheme is symmetry dependent for any different like space group symmetry. You will find the different transformation matrix and the splitting scheme. So luckily, if you do this by hand, it can be very boring. So luckily, so now in our software, we can actually do this automatically. You don't have to worry about that. So all of this actually can be done with mathematical rigor. So as long as you so we have the database to enumerate all the possible space group to subgroup relations, and also so in this case, so you can actually enumerate all the possibilities. Okay, so after we have that, I can just give you another working example to explain why do we need the symmetrization in structure generation. So for instance here, so I'm giving you a case of like Lennard-Jones clusters. So basically, the problem is to arrange the atoms into nanoparticles in the 3-dimensional space. So the interaction between the atoms can be described by the simple Lennard-Jones potentials. So how do we do this? So let's okay, if we just do the random sampling with the scheme, you can see how it look like. So I did the following. So first of all, we generate 1,000 random structures, and then we optimize them. So it's very easy. So after that, so you can see how the difference between different like random symmetrization protocols. So if we don't enforce the symmetry when we generate the random structure, that means we generate the purely random structures. You see the distribution of the energies after optimization. So usually when you do this, you will see these structures are actually the energy of the structures are arranged in a very tight space. So, but if you allow each structure to possess some like initial symmetry, point group symmetry, then you do optimization, you see the energy distribution is much wider. That actually confirms my point in the beginning. So so it actually brings more diversity. Also, when it tries to widen this distribution. So by doing this, you have chance to hit like high energy structures, but in the same time, you also have you increase the chance to hit the low energy structures. You see, in this case, you can actually you can generate you can actually find, you can hit the ground state structure much more frequently than the purely random approach. Okay, this just another two examples for Lennard-Jones particles with two different with different numbers. You see, yeah. So every time, so you can really, so when you do the search, so symmetrization is really beneficial to the efficiency of the search. Okay, so another thing is like, so because pi crystal is very because it's very flexible, so we are also playing with like the optimization algorithms. So for instance, we are actively developing some like optimization algorithms. So to actually push the distribution of the energy to the low energy space. So because of the time restriction, I will skip this topic. Okay, just to summarize, so what we can do with the new code. So PyCrystal is a package aimed to handle the crystal symmetry. So we can start with some input constraints. So from the user side, you just need to tell, in order to generate the crystal, you need to tell them the program the stoichiometry. Also, you tell the program the space group. Optionally, you can also tell the program the cell parameters. After that, it will generate a random structures which satisfy this constraint. And then we have some like internal code to do the optimization. So we interface this code with like different calculators. So you have choice to choose DFT, force field, and also machine learning style force field to do the pre-optimization based on different algorithms. So gradient descent, conjugated gradient, quasi-Newton, or any or some other stochastic methods, and then you get the optimized structure. But in also, if you want to modulate the structure after optimization, you can perturbate the structures by preserving the symmetry or following this group subgroup relations. So last, I want to mention that, so we have I know like there are several other packages which can generate the random structures with desired symmetry as well. But by far we provide the largest flexibility. So you can deal with the symmetry objects from 0D to 3-dimensional space. Also, you can do both atomic and molecular crystals. Yeah, so that's basically another overview of the functionality of the code. Okay, so a little bit about the development timeline. So we launched this project just 2 years ago. So when I had a master student, Scott, so I assigned this project to them in the beginning. So I thought it was just fun. So he works very hard and then got this package. And then later on, so it's very interesting. So because this is open source project, we actually, this project attracted several other people outside the group So they volunteered to develop some functionality to improve their code, for instance, X-ray diffraction pattern or many other things. So the group subgroup relations of the group subgroup transition function was just implemented a few days ago. So far we have already received like over 8,000 downloads of the package. So it's getting popular in this community. So as I said, so we have internal contributors from my group. We also have contributors outside the group. So if you are interested, so you're interested in using this software, you can easily install this as long as you know how to run your Python, how to run Python in your computer. So if you are interested in the development, you can also fork the repository and also implement some new function and merge it to our code. Okay. How much time do I have?
I think you have 2 more minutes, but if you want to continue, it's not a problem.
Okay, I see. So actually, I think I'm about to finish. So yeah, last I would like to close this presentation by thanking people who are involved in this project. So also a quick announcement. So I'm currently looking for like 1 or 2 postdocs. So in the development of the PyCrystal code, also development of force field, and also molecular simulation. If you are interested or you know some people who may be interested, please let me know. Okay, I think that's all. So for those of you who want to try this program, so you can easily find our GitHub work page. Also, there are many links. So we have documentation. So you can easily actually do some productive work by following these documentations. Okay, I think that's all.
Thank you, Chang. And there are a couple of questions in the chat.
Let me check this. So, okay, I saw 2 questions asked by Busan Wang. Yeah, so the first question is if it's possible to interface PyCrystal with USPEC. Actually, that's a brilliant idea. I think it can be done easily. So because the way which I construct the PyCrystal actually follows exactly the philosophy of USPEC. So you can just consider the PyCrystal as an additional library for USPEC, and then you can easily access the functionality of PyCrystal inside the USPEC. You can also you can use this like degeneration, also variation operations in through PyCrystal. The second question is, could you simply have an introduction about the main difference of random generating algorithms between PyCrystal and the USPEC? That's a good question as well. So because I used to be the chief developer of USPEC, I know how USPEC generated the random structures. So basically, in terms of like, so basically we follow the same idea. So, but they, in the current USPEC version, if I'm not mistaken, so it is still used the old Fortran code to generate the random symmetrical crystals. So also it has some limitations. It cannot do, for instance, it cannot do the molecular crystals with special Wyckoff size. Also, it cannot do the group subgroup relations. So PyCrystal basically is built upon the idea of structure generation in USPEC, but it has more functionalities. So that's the difference. So in terms of functionality, PyCrystal is more versatile. Okay, I got some congratulations from Jules. So yes, so this PyCrystal is just to let you know, PyCrystal is an open source package. So everyone has the freedom to contribute to the code. You can change this code. So everything is completely open. So if you want to actually address your opinion, just let me know. You can easily go to the GitHub page, so which I'm sharing here. So you can just do whatever you want. Let me know. Any other questions? Guys, I know you might be exhausted, but for me, it's just the beginning of the day. I have enough energy to handle the questions. So if you are tired, so okay. Okay, if you are tired, so probably you can leave the meeting. Otherwise, so yeah, please ask your question. Okay, I have one question from Ninan. So what are the future goals of PyCrystal? Oh, we have several possible directions. So one direction is to, okay, I have some, maybe I can share this again. So one possible direction is to, we consider this is a package for manipulating the crystal symmetry. So we will consider to generate some structure with a 4-dimensional superspace group, which will be useful for studying the quasi-crystals. And also we are trying to add more functionalities to the to play with the structure variation. So I told you, so now we can generate the structures with the subgroup symmetry. But in later on, we may also develop some function to generate the structures which has the supergroup symmetry. So everything is about the symmetry. Also, another possible direction is to merge this code to any existing crystal structure prediction package. So like USPEX, of course. So yeah, so I will be very happy if someone can merge this to USPEX. Okay. The question from Dimitri. So thanks for a very interesting talk. When generating the atomic coordinates in PyCrystal within a user-defined lattice, is it possible to define only a part of lattice parameter and then let the PyCrystal to determine the remaining of parameters randomly? Actually, this is possible. We don't have this function yet, but since we have very flexible framework, so if some people is interested in this direction, we can easily implement this option within only a couple of days. Second question from Dimitri. Is it possible to change the number of attempts or limit the execution time for the structure generation routine? Yeah, again, so we have a very flexible framework. So you can generate, of course, you can decrease or increase the number of attempts or limit the execution time. This can be done easily. I know sometimes probably it will stuck when you want to generate some complicated crystals. It may get stuck because Python is not really designed for the high performance computing. But I think usually I did a lot of tests. So for instance, if you want to generate some structures with over 100 structures, then you can still get this done in a reasonable time. So probably less than 1 minute. Usually it will be less than 1 minute. Okay. Another question from Chi. So can you explain the they transition from FD3M 48A to I41MD AMD 4A. Why the number changed? Yes, this is a very good question. So basically, why the number changed? Because you see, we are talking about a crystal. Crystal, in principle, the crystal should have infinite numbers. So because it will be repeated in the entire three-dimensional space. So now we but when we talk about the number of atoms per unit cell, is because the purpose of this is to simplify the description. So we choose some like a unit cell, and then we count the number of atoms in the unit cell. If you have different space group symmetry, so the number can change. Yeah, the number actually, you can allow this to change. Okay. One more question from Lausanne. So could you please elaborate a little bit more on the molecular crystal part regarding the symmetrical rotations? Okay. Probably you are asking for this figure. So what do we do here? So in order to generate this crystal with the CMC 2-1 symmetry, so as I already told you, so if we pick the Wyckoff size 4A, so then Wyckoff size 4A will ask you to satisfy this Wyckoff positions. So that means you have freedom in Y and Z axis, but you don't have freedom at 0 or at the X axis. So X axis will be, has to stay at 0 or 1/2 positions. And then, so then we place the molecules, and by letting the center of the molecule occupying these positions, you see this is 0 when X is equal to 0. This is when X is equal to 1/2. And on top of that, so we also need to satisfy the side symmetry orientation. The crystal, you cannot just randomly place the crystal in any orientation. You have to put the orientation in this way. So in this way, you see, when you rotate the molecule, you can rotate this molecule 300 degrees by following this rotational axis. But if you rotate the molecule in other axis, along other axis, the symmetry will be broken. Yeah, that's the main idea of this. Okay, any other questions? If you guys want to have another questions, probably because now, as I said, so it's just the beginning of the day in Las Vegas. So probably we can open a breakout room. So I can show how to run the code. I can show you how to run the code. So if you want. Otherwise, probably we should let the host to close the meeting. And I know the host must be very tired after one day long program. Okay, I will stop sharing my screen.
Okay, I think, Alice, we can probably open the breakout room, and thank Chang for the great presentation. And so I guess this session is over for today, and have fun with Pixtal, those who will go to the breakout room.
You have just opened the breakout room.
So how do I enter the breakout room? Just raise my hand, right?
No, actually, you must have this button to join it. It's called
Wait.
chat room.
In the chat, I see.
Yeah, it's the room is called chat room. Maybe try three dots more. It's down.
Oh, I see. Oh no, I don't have this. I don't think I have this option.
Vladimir, can you see the breakout rooms?
I can see it, but I'm the co-host. But I think that all of the people should be able to see it.
You're not the co-host anymore. You must see.
No, I can't see anything. I saw the breakout rooms button before, but now I can't see anything.
Actually, there is a person who managed to join it.
Okay, so if it's difficult, maybe I can arrange I can arrange like a meeting room by myself. I can then I posted the link here.
I can stop the YouTube broadcast and
Yeah.
everyone who'd like to
Okay,
have a discussion can stay here instead of the chat room.
Okay, yes, you can make Chang a host and just stop the recording. And Chang will stop the session when they finish.
Yeah.
Chang, you're the host now.
Okay.
Can you see the changes?
Yes, I got a notification now. I'm the host. Oh, actually, I see the breakout room now.
The problem is that every participant should see it, not just the host.
Okay, yeah.
And I haven't stopped the YouTube stream. No, I can't do this. Please stop it. It's on the left.
Oh, okay. Stop recording, right?
Above. Yes.
Okay.
Thank
okay,
you.
I will just.